Hello there and welcome to Physics with William, where the universe is allowed to be strange, the explanations are allowed to take their time, and even the smallest particles can settle in for a quiet evening without being hurried into a conclusion. Tonight, we're going to look at a form of matter that sounds as though it belongs in a science fiction cabinet, somewhere between a crystal that remembers the future and a teapot powered by dark energy. It is called a tetraquark. The name may sound technical, but its basic idea is surprisingly simple. A tetraquark is a particle associated with four quark constituents, usually described in its minimal arrangement as two quarks and two antiquarks. That sounds tidy enough. 4 tiny pieces, 1 small particle, and perhaps we can all go home early. But the deeper question is not simply how many pieces are present. It is how those pieces are connected, why they remain together even briefly, and what their existence tells us about the rules from which ordinary matter is built. Before we move any further into that very small and very crowded world, I would love to know where you are listening from tonight. Are you somewhere quiet with the lights low and the day beginning to loosen its grip? Or are you listening in the middle of an afternoon while pretending that a calm discussion of particle physics is definitely part of your work schedule? And while we're thinking about matter, take a moment to notice the things around you. Perhaps there is a pillow beneath your head, a phone in your hand, a cup nearby, or a wall doing its dependable best to remain a wall. All of those objects seem solid, familiar, and uncomplicated. Yet every one of them is made from structures nested inside structures, with most of their apparent simplicity hiding a much stranger foundation. If you find these slow journeys through physics soothing, interesting, or simply useful for persuading a busy mind to stop rearranging tomorrow's problems, I would be very grateful if you gave the video a like and subscribe to the channel. It helps this quiet corner of science reach other curious listeners who may also enjoy learning about the universe at a pace normally reserved for cooling tea. And as always, there is no need to remember every particle name or every scientific detail. You're not preparing for an examination. No one is about to burst into the room and demand that you explain the strong interaction before breakfast. You can simply follow the story for as long as you like, allowing the ideas to become softer as you become sleepier. The story begins with a picture of matter that once seemed almost wonderfully manageable. During the 20th century, physicists learned that the protons and neutrons inside atomic nuclei were not truly elementary. They contained smaller objects called quarks. Quarks appeared in several types, with names such as up, down, strange, charm, top and bottom. The names were not intended as descriptions of personality, which is probably fortunate. A charm quark is not especially persuasive, and a strange quark is no more likely than the others to collect unusual lamps. These labels describe different varieties of the same fundamental kind of particle, each with its own mass and other physical properties. Quarks rarely appear alone. They're governed by the strong interaction, the part of nature described by quantum chromodynamics. This interaction binds quarks into composite particles called hadrons. For many years, the most familiar hadrons fitted into 2 broad arrangements. There were baryons, including protons and neutrons, which could be described using 3 quarks, and there were mesons, which could be described using 1 quark and 1 antiquark. It was a neat arrangement, almost suspiciously neat, like opening a kitchen drawer and finding that every spoon has agreed to lie in the same direction. The proton, for example, contains an arrangement of 2 up quarks and 1 down quark. The neutron contains 2 down quarks and 1 up quark. These 2 particles make up nearly all the mass of the ordinary material around us. The electrons in atoms are important too, of course, especially for chemistry and electricity, but most of the mass in your chair, your blanket, and the planet beneath you comes from protons and neutrons. Those protons and neutrons, in turn, are restless systems of quarks, antiquarks, and gluons, with energy moving and interacting inside them. Matter looks calm at our scale because we are much too large and much too slow to see the commotion. Mesons offered the second familiar pattern. A quark could pair with an antiquark, creating a short-lived particle with its own mass, charge, and ways of decaying. Many mesons were discovered, and although the catalogue grew increasingly busy, the underlying arrangement remained understandable. 3 quarks for a baryon, 1 quark and 1 antiquark for a meson. It was not the whole of particle physics, but it was a useful rulebook. If the microscopic world had been a restaurant, physicists thought they had identified the 2 standard table arrangements. There was always an important caution, however. The theory of the strong interaction did not plainly announce that quarks were permitted to gather only in 2s and 3s. More elaborate combinations could also satisfy the deeper requirements of the theory. 4-quark arrangements were discussed. 5-quark arrangements were discussed. Even larger groupings were considered. The mathematics did not close the door. But nature seemed reluctant to send a clear invitation. For decade after decade, the particles observed in experiments fitted mostly into the ordinary meson and baryon families. The complicated possibilities remained in theoretical conversations, appearing in papers and calculations, but refusing to stand still long enough for a confident photograph. This is where the Tetraquark becomes important. It did not merely add another name to an already crowded particle list. It challenged a habit of thought. Physicists had become extremely successful at describing hadrons through the simplest quark combinations, and success can make any rule feel more permanent than it really is. Then unusual particles began appearing in experimental data. Their masses, electric charges, decay patterns, or other properties did not fit comfortably into the expected slots. Some contained combinations that an ordinary quark and antiquark meson simply could not provide. The old filing cabinet still worked for most particles, but suddenly several documents were sticking out at impossible angles. Imagine that you had spent years studying animals on an island where every creature had either 2 legs or 4. You might know, in principle, that a 6-legged creature was biologically possible. You might even sketch one in a notebook. But if none had ever been seen, the island would still feel like a place governed by 2s and 4s. Then one evening, something with 6 legs walks calmly past the research station and steals a sandwich. The laws of biology have not changed. What has changed is your understanding of what those laws actually produce. Tetraquarks played a similar role in the study of the strong interaction, though so far none has been accused of stealing lunch. The word tetra means 4, but even that simple name can mislead us if we imagine 4 hard beads locked together in a tiny box. Quarks are quantum objects. A hadron is not a miniature mechanical model with coloured balls sitting in fixed positions. Its interior is a shifting field of energy and interaction. Gluons carry the strong force between quarks. Quark and antiquark pairs can briefly appear and disappear within the system. The identity of a particle comes not from a frozen photograph of its contents, but from the total pattern of its quantum properties and the way it behaves. So when physicists say that a tetraquark contains 2 quarks and 2 antiquarks, they are describing the minimal quark content needed to account for the particle's observable properties. They are not necessarily claiming that exactly 4 objects sit quietly inside and nothing else happens. Particle interiors are rarely that considerate. The real mystery is the arrangement of the dominant components. Are all 4 quarks bound tightly into one compact structure? Are they paired into 2 mesons that remain loosely attached, rather like 2 ordinary particles forming a fragile molecule? Do 2 quarks cluster together, while the 2 antiquarks form a corresponding cluster? Or does the object shift between several descriptions, with no single familiar picture capturing everything it is? Those possibilities are not small details. They represent different ways in which the strong interaction may organize matter. A compact tetraquark would show that 4 quarks can form a genuinely integrated hadron, a structure not easily divided into ordinary particles. A molecular tetraquark would show how known hadrons can cling together through residual effects of the strong force, much as atomic nuclei are held by forces left over from the deeper interactions among quarks. A state influenced by several configurations would remind us that nature is not required to choose. the diagram we find easiest to draw. This uncertainty is part of what makes tetraquarks so interesting. In popular descriptions, new particles are sometimes presented as though scientists discover a tiny object, read the label attached to it and place it neatly on a shelf. Real particle physics is less accommodating. Detectors do not see quarks directly. They record showers of particles produced in high-energy collisions. Physicists reconstruct tracks, measure energies, identify decay products, and search for patterns appearing more often than ordinary background processes would allow. A new particle may reveal itself as a narrow rise in a distribution, a small hill made from thousands or millions of events. It is less like spotting a new bird and more like concluding that an invisible bird exists because a forest microphone keeps recording the same unfamiliar call. Even after a signal is established, the interpretation can remain difficult. A peak in the data may indicate a genuine bound, state, or resonance, but deciding what kind of internal structure produced it can take years. Different models may explain the same mass. Different arrangements may predict similar decays. One experiment may see a state clearly while another sees only a hint. The particle itself may survive for such a short time that asking what it looks like becomes almost philosophical. Yet short-lived does not mean unreal. A flash of lightning is brief, but it can still rearrange a tree. Tetraquarks belong to a wider family often called exotic hadrons. Exotic in this context does not mean supernatural or imported from a distant universe. It means that the particle does not fit the simplest traditional patterns of a quark paired with an antiquark or three quarks grouped together. Some exotic hadrons are tetraquark candidates. Others are pentaquark candidates, involving 4 quarks and 1 antiquark in their minimal content. There are also ideas involving excited gluonic fields, particles made largely from gluons, and mixtures that refuse to respect the tidy boundaries of our classroom categories. The word exotic can make these particles sound like rare decorations added to the edge of physics. In reality, they touch one of its central problems. We know the basic theory governing quarks and gluons. Quantum chromodynamics has passed demanding experimental tests. At very high energies, where quarks interact over extremely short distances, calculations can be remarkably precise. But at the lower energies where quarks bind into hadrons, the strong interaction becomes extremely difficult to solve. The theory is known, yet its consequences are not always easy to calculate. It is a little like possessing the complete rules of chess, while still being unable to predict the position on the board after 1,000 moves played by pieces that occasionally create more pieces. This difficulty arises partly because the strong interaction behaves unlike the forces most familiar in everyday life. Quarks carry a property physicists call color charge. The word color is only a label and has nothing to do with visible red, green, or blue light. The strong interaction acts among these color charges, and observable hadrons must form combinations that are neutral in the relevant color sense. Ordinary mesons and baryons achieve this neutrality in familiar ways. Tetraquarks can also form an overall neutral combination, but there may be several routes to that result. Each route changes how the internal components attract, repel, rearrange, and decay. The strong force also has the unusual property that quarks become harder to separate as the distance between them grows. Pulling 2 quarks apart does not eventually free them in the way pulling 2 magnets apart does. Instead, enough energy accumulates to create new quark and antiquark pairs, producing new hadrons. This is called confinement. It is why no one has placed a single quark in a jar, although it is probably wise not to leave an empty jar labelled single quark on a laboratory table. Someone will ask questions. Because quarks are confined, physicists learn about them indirectly through the composite particles they form. Every new hadron is therefore a message from the strong interaction. Ordinary hadrons tell us about the most common arrangements. Tetraquarks test the less familiar possibilities. They allow scientists to ask whether the strong force prefers certain pairings, how heavy quarks influence stability, why some combinations form narrow states while others dissolve almost immediately, and where the boundary lies between one particle and two particles temporarily sharing the same quantum space. Heavy quarks are especially useful in this search. Charm and bottom quarks are much heavier than up and down quarks. Their mass can make parts of the system easier to model, not easy in the ordinary sense, but easier in the way that carrying 4 shopping bags is easier than carrying 5. Many of the Tetraquark candidates discovered so far contain charm quarks, charm antiquarks, bottom quarks, or bottom antiquarks. These heavy components can act like anchors around which lighter quarks and gluons move. They also produce distinctive decay products that detectors can identify with impressive precision. One particularly striking class contains more than one heavy quark, without matching every heavy quark with its own heavy antiquark. Such particles cannot be mistaken for a conventional meson in the usual sense, because their minimal quark content demands something beyond a single quark and antiquark pair. Other candidates contain a charm quark and a charm antiquark along with 2 lighter constituents. These can be more ambiguous because the heavy pair might resemble the core of an ordinary charmonium meson, while the remaining components influence the surrounding structure. Nature has provided a varied collection, but it has not included an instruction manual. That lack of an instruction manual is not a failure, it is the reason the field is alive. Each new measurement narrows the possibilities. Physicists compare masses, lifetimes, charges, spins, and decay routes. They examine whether a state lies just below or just above the energy needed to split into 2 ordinary hadrons. A state very close to such a threshold may behave like a molecule. A state far from it may support a more compact interpretation, but even these clues must be handled carefully. Quantum systems are fond of borrowing features from several categories at once. The Tetraquark, therefore, changes what matter can be, not because it overturns the strong interaction, but because it reveals more of what the strong interaction was capable of all along. The theory had room for complex hadrons. Experiments had to show that nature actually used that room. Once convincing examples began to accumulate, the old picture of hadrons as only simple pairs and trios could no longer serve as the whole story. It remained a very good first lesson, but it became a doorway rather than a destination. There is something quietly humbling about that. The matter around us appears stable because a few combinations dominate ordinary life. Protons endure. Neutrons remain safely inside many nuclei. Electrons arrange themselves around atoms. Chemistry builds molecules, cells, oceans, furniture, and occasionally a biscuit that leaves far more crumbs than its size should permit. From our perspective, matter seems to have settled on a reliable design. Yet when enough energy is concentrated into a collision, the deeper theory displays a much wider imagination. Inside particle accelerators, protons are pushed to extraordinary speeds and brought into collision. The energy of their motion becomes a brief opportunity for new particles to form. Most vanish almost instantly, decaying into lighter and more stable products. Detectors surround the collision points, recording the aftermath with layers of sensors. From this debris, researchers reconstruct events that occurred at scales far below direct vision. The Tetraquark appears not as a glowing speck, but as a repeated relationship among the particles left behind. It may seem strange to call something a particle when it exists only fleetingly and must be inferred from its decay. But nearly every unstable particle is known in this way. We recognize it through consistency. The same mass appear again and again. The same decay pathways recur. The statistical signal grows until chance is no longer a reasonable explanation. A particle is not required to be permanent. It is required to be a real, reproducible feature of nature. And that brings us to the central puzzle we will follow through this journey. A tetraquark is easy to define loosely and difficult to understand deeply. Saying that it involves 4 quark constituents is only the beginning. We still need to know what quarks are, why antiquarks are not simply quarks moving backwards in a tiny corridor, how gluons bind these objects, and why the familiar families of hadrons became so successful that more complicated arrangements once seemed almost unnecessary. We will also need to understand how scientists recognize a tetraquark when no detector can simply take a picture of one. We will meet unusual signals, disputed interpretations, and particles whose electric charges reveal that the ordinary meson explanation cannot work. We will see why some tetraquarks may be compact, while others may resemble delicate hadronic molecules, and we will discover that the boundary between these descriptions can be less like a wall and more like a foggy path across a field, visible in places and uncertain in others. For now, it is enough to hold on to one quiet idea. Matter is not limited to the arrangements that happen to be common around us. The proton and neutron are essential, but they are not the full vocabulary of the strong force. Mesons are plentiful, but they are not its only short-lived sentences. Tetraquarks show that quarks can participate in richer patterns that were allowed by theory yet remained hidden in experiments for years. Perhaps that is worth remembering whenever nature seems overly familiar. A table looks like a table because countless microscopic structures behave consistently. A stone rests quietly because its atoms have settled into stable arrangements. Your own body holds together because matter follows dependable rules. But dependable does not mean simple, and familiar does not mean complete. Beneath the ordinary world is a set of interactions capable of building objects that earlier generations of physicists could discuss but not confidently confirm. So settle a little more comfortably, let the day become quieter, and imagine the interior of matter not as a set of hard little balls, but as a restless society of fields, charges, and possibilities. Somewhere within that society, four-quark constituents can gather into a single observable state, remain together for an unimaginably brief interval, and leave behind enough evidence to force us to redraw the map. To understand how such a gathering is possible, we first need to step back from the tetraquark itself and look carefully at the pieces from which it is named. Quarks and antiquarks are often introduced as though they were tiny building blocks, but they are stranger than ordinary blocks, impossible to isolate, governed by a force that grows more demanding when separation is attempted, and organized by a kind of charge that physicists borrowed the word color to describe. That is where the real structure of this story begins. To understand how a tetraquark can exist, we first need to become familiar with the objects hiding inside its name. Quarks and antiquarks are often introduced as the smallest building pieces of protons, neutrons, and many other particles. That description is useful, but it can also create the wrong picture. A quark is not a tiny grain of material with a hard surface. It is not a miniature marble tucked inside a slightly larger marble. According to our best current theories, a quark is an elementary quantum particle. Experiments have not revealed any smaller structure inside it. As far as physicists can presently tell, there are no little gears, shells, or even smaller quarks waiting beneath the surface. This makes the phrase pieces inside the pieces slightly troublesome, because quarks do not sit inside protons in the way raisins sit inside a cake. A raisin has a clear boundary. You can remove it, place it on a plate, and wonder why someone put raisins in the cake at all. A quark cannot be removed so politely. It is bound by the strong interaction, and the harder we attempt to separate it from the other quarks, the more energy the system stores. Eventually, that energy produces new particles rather than releasing a single isolated quark. Nature seems perfectly willing to rearrange the entire tray, but it refuses to hand us one raisin. There are 6 known types of quark. Physicists call these types flavors, another word that should not be taken too literally. No experiment has established whether a strange quark tastes different from a charm quark, and it would be unwise to volunteer for the investigation. The 6 flavors are called up, down, strange, charm, top, and bottom. These names grew from the history of particle physics rather than from a grand naming plan. Scientists discovered unfamiliar patterns, needed labels, and apparently decided that dignity had already survived words such as electron and neutron, so it could probably survive charm. The up and down quarks are the lightest and the most important for the ordinary matter around us. Protons contain 2 up quarks and 1 down quark in their simplest description. Neutrons contain one up quark and two down quarks. Protons and neutrons form atomic nuclei, and atoms form nearly everything we handle in daily life. Your bed, the walls, the air, and the device playing this video all depend on combinations of up and down quarks. If those two flavors were removed from the universe, furniture would become the least of our concerns. The strange quark is heavier than the up and down quarks. It appears in unstable particles produced naturally in cosmic ray collisions and artificially in laboratories. The charm quark is heavier still, followed by the bottom quark and then the top quark, which is by far the heaviest. The top quark is so short-lived that it decays before it can settle into a hadron. The other 5 flavors can participate in bound systems, although the heavier ones generally appear only under energetic conditions and disappear quickly through decay. Heavier does not necessarily mean physically larger. In particle physics, mass and size are not interchangeable. A top quark has far more mass than an up quark, but neither has shown a measurable internal radius in experiments. Their different masses describe how strongly their fields contribute energy and how they behave in interactions. This is one of those places where everyday intuition quietly places its coat over a chair and leaves the room. Quarks also carry electric charge, though not in the whole units familiar from protons and electrons. Up charm and top quarks each carry positive 2/3 of the proton's electric charge. Down strange, and bottom quarks each carry negative 1/3. These fractional charges combine inside hadrons to produce the whole charges we usually observe. 2 up quarks and 1 down quark together give the proton its positive charge. 1 up quark and 2 down quarks together give the neutron no overall electric charge. For a long time, fractional electric charges seemed deeply peculiar. Scientists were accustomed to particles carrying one full positive or negative unit. The suggestion that protons and neutrons contained objects with thirds of a charge initially sounded like an accounting system designed by someone who had misplaced the rest of the invoice. Yet the quark model successfully explained patterns among known particles, and later experiments revealed evidence of point-like charged constituents inside protons. The fractions were strange, but nature showed no interest in rounding them up for convenience. Every quark has an antimatter partner called an antiquark. An antiquark has the same mass as its corresponding quark, but several of its quantum properties are reversed. Its electric charge has the opposite sign. An anti-up quark carries negative 2/3 of the proton's charge, while an anti-down quark carries positive 1/3. Antiquarks are not defective quarks, nor are they ordinary quarks that have become unhappy with their career choices. They're genuine particles with well-defined properties of their own. Antimatter is sometimes imagined as matter with negative mass, but that is not what the word means. An antiquark has positive mass and responds to energy and motion in the usual physical way. What makes it antimatter is the reversal of charges and other quantum numbers. When a quark meets its matching antiquark, the pair may annihilate, converting their energy into other particles. But the word annihilate can be misleading too. Nothing simply disappears. Energy, momentum, electric charge, and the other conserved properties still have to balance. The ingredients change form, while nature keeps extremely careful records. A quark and its own matching antiquark can therefore destroy their original identities during an interaction, but this does not mean that every hadron containing quarks and antiquarks vanishes immediately. Ordinary mesons are made from a quark and an antiquark, and many survive long enough to be measured clearly. The rate at which they decay depends on their flavors, masses, internal states, and the interactions available to them. Some processes are strongly allowed and happen rapidly, others rely on the weak interaction and take much longer by particle standards. This becomes especially important when we approach tetraquarks. A tetraquark contains quarks and antiquarks in the same overall system. At first glance, that might sound like inviting equal amounts of matter and antimatter into a very small room and expecting everyone to remain calm. Yet the flavors may differ. The components may be arranged in ways that suppress immediate annihilation, and the whole object may occupy a quantum state with its own permitted and forbidden decay routes. Particle physics is less like placing substances in a bowl and more like arranging musicians who are allowed to play only certain notes. Electric charge is only one of the properties carried by quarks. To understand why they bind together, we need another kind of charge called color charge. This is the charge involved in the strong interaction. Physicists use the labels red, green and blue for the three forms of quark color, along with corresponding anticolors for antiquarks. These names have nothing to do with visible light. A red quark is not actually red. You could not illuminate one and match it to a curtain. The color labels describe mathematical relationships within quantum chromodynamics, the theory of quarks, gluons, and the strong interaction. The word chromodynamics roughly refers to the dynamics of color, but the color is entirely symbolic. Physicists could have called the charges 1, 2, and 3, or perhaps tea, coffee, and cocoa. Red, green, and blue offered a helpful analogy because three visible colors can combine to make white light, just as three different color charges can combine into an overall color, neutral hadron. Observable particles must be color neutral. A baryon, such as a proton, can achieve this through three quarks carrying three different colors. A meson can achieve it through a quark carrying one color and an antiquark carrying the matching anticolor. The total object has no exposed color charge. This does not mean the interior is empty of color activity. The color charges are constantly interacting and changing. It means that from outside, the combination is neutral. Tetraquarks can also form color-neutral combinations, but they have more than one possible internal arrangement. Two quarks might combine into a pair with a particular color relationship, while two antiquarks form the balancing partner. Alternatively, each quark might pair mainly with an antiquark, creating a structure resembling two mesons held near each other. The entire object must remain color neutral, but the route by which it achieves that neutrality can vary. This flexibility is one reason tetraquarks are so difficult to describe with a single simple picture. The carriers of the strong interaction are particles called gluons. Their name comes from the idea that they glue quarks together, although this glue behaves unlike anything sold in a tube. Gluons have no electric charge and no rest mass, but they carry color information. This makes them very different from photons, which carry the electromagnetic interaction, but do not themselves carry electric charge. Because gluons carry the kind of charge on which they act, they can interact with one another. A photon does not normally emit another photon merely because both are involved in electromagnetism. Gluons, by contrast, can exchange color with other gluons and participate in complicated networks of self-interaction. This gives the strong force much of its unusual behavior. The glue is capable of gluing itself, which sounds useful until one imagines opening the container. When a quark emits or absorbs a gluon, its color can change. A red quark might become blue by emitting a gluon carrying the appropriate combination of color and anticolor. The labels change, but the complete system continues to satisfy the conservation rules. Inside a proton, color is not assigned permanently to one quark like a seat number. It is exchanged continuously through gluon activity. The proton remains color neutral as a whole, while its interior behaves more like a crowded station, where everyone keeps swapping tickets. The strong interaction has another surprising feature. At extremely short distances, quarks behave more nearly as though they are free. This property is called asymptotic freedom. When quarks are very close together or examined at very high energies, the effective strength of their interaction becomes weaker. As the distance grows, the interaction becomes stronger. This is almost the reverse of the everyday forces we know best. Consider gravity. The farther you move from Earth, the weaker its gravitational pull becomes. Electric forces also weaken with distance. The strong interaction between quarks does not follow that simple pattern. Pulling quarks apart increases the energy stored in the color field between them. A common analogy imagines a flexible cord stretching between the quarks. The farther the cord is pulled, the more energy it contains. But even this analogy has limits, because the real system is a quantum field rather than a physical cord. If enough energy is added while separating quarks, the field can produce a new quark and antiquark pair. Instead of leaving one quark alone, the system breaks into new color-neutral hadrons. It is rather like trying to pull one end from a piece of elastic material, only to discover that the material creates two new ends and leaves you holding two complete pieces. You began with one hadron, supplied energy, and finished with several hadrons, but never with a lonely quark looking for somewhere to sit. This phenomenon is called confinement. No isolated quark or gluon has been observed under ordinary conditions. They appear bound inside hadrons. In extremely hot and dense matter, such as the quark and gluon plasma produced in heavy ion collisions, quarks and gluons are no longer confined inside individual protons and neutrons. Even there, however, the state exists only briefly. As it cools, the quarks and gluons form hadrons again before reaching the detectors. Confinement means that physicists cannot study a quark by placing it alone in an instrument. Instead, they examine the effects quarks produce inside larger systems. High-energy particles can be fired into protons, revealing how their momentum is distributed. Collisions can produce sprays called jets, which begin with energetic quarks or gluons, but develop into streams of ordinary hadrons before they are measured. The original coloured particle is never delivered directly to the detector. It leaves behind a family of colour-neutral descendants. The interior of a proton is therefore more complicated than the phrase 2 up quarks and 1 down quark suggests. Those three are called the valence quarks because they determine the proton's main identity and electric charge. But the proton also contains gluons and a constantly changing sea of additional quark and antiquark pairs. These pairs can emerge through the energy of the strong fields and disappear again through interactions. The proton is not an empty container holding three permanent objects. It is a busy quantum system whose overall properties remain stable even while its internal activity continues. Most of the proton's mass does not come directly from adding the small masses of its valence quarks. It arises from the energy of the strong interaction, the motion of quarks and gluons, and the dynamics of confinement. This is a remarkable fact. Nearly all the mass of ordinary visible matter is connected not simply to the intrinsic masses of its smallest components, but to energy stored in their movement and interactions. A solid object feels heavy because its microscopic contents are doing far more than sitting still. Antiquarks are part of this activity even inside ordinary matter. A proton is not made of antimatter in the everyday sense, because its net quantum properties identify it as matter. Yet temporary quark and antiquark pairs contribute to its internal structure. This reminds us that quantum particles are not best understood as permanent little occupants assigned to fixed rooms. The proton is defined by the full state of its fields and by the properties that remain when all the internal fluctuations are considered together. Quarks also possess a property called spin. Despite the name, spin does not mean that a quark is physically rotating like a small planet. It is an intrinsic quantum property affecting how the particle behaves under rotations and how it combines with other particles. Quarks belong to a class called fermions, and their spins help determine which arrangements are allowed. When several quarks occupy a hadron, their spins, flavors, colors, and motion must fit together consistently. This creates a large variety of possible particles. The same quark flavors can sometimes form different hadrons depending on how their spins and internal motion are arranged. A particle can occupy a lower energy state or an excited state, much as an atom can hold its electrons in different energy configurations. Excited hadrons usually decay rapidly into lighter particles, but while they exist, they are distinct states with measurable masses and properties. Quark flavors can also change through the weak interaction. A down quark can transform into an up quark in a process involved in radioactive beta decay. Strange charm, bottom and top quarks can decay through related transformations, eventually producing lighter particles. The strong interaction binds quarks, but it does not freely change one flavour into another. The weak interaction handles those transformations, showing once again that several forces may be involved in the life and death of a single hadron. The heavier flavours are especially useful when studying unusual combinations. Charm and bottom quarks are heavy enough to give a particle distinctive features, while still living long enough to form bound systems before decaying. A tetraquark containing charm or bottom can leave recognisable decay products, allowing researchers to reconstruct what happened. Heavy quarks also move more slowly within some hadrons than light quarks do, which can make parts of the theoretical problem more manageable. None of this means the interpretation becomes easy. A particle containing a charm quark, a charm antiquark, and two light constituents may resemble several structures at once. The charm pair might form a central component surrounded by light quark activity. The four constituents might combine compactly, or the system might resemble two conventional mesons attracted to each other. The same underlying quarks can support different arrangements, just as the same collection of musicians can form a quartet, two duets, or a group in which one person has forgotten which piece everyone agreed to play. What matters is that quarks are not merely objects placed beside one another. Their colours, flavours, spins, masses and motion determine how the strong interaction can organise them. Antiquarks add matching possibilities with reverse charges. Gluons continually carry colour between them. Confinement prevents the individual ingredients from escaping. Every hadron is therefore a complete colour-neutral pattern, rather than a loose bag of parts. This is why the discovery of tetraquarks required more than counting 4 visible objects. The quarks themselves are never directly seen. Scientists must study the complete particle, observe how it forms and decays, and infer the smallest arrangement capable of explaining its properties. In some cases, an unusual electric charge makes the conclusion especially strong. A conventional quark and antiquark meson cannot produce every possible combination of charge and flavour. When a particle displays properties that demand at least 2 quarks and 2 antiquarks, the old explanation runs out of room. Before such evidence appeared, physicists already knew that the theory allowed richer combinations. Quarks and antiquarks could, in principle, be arranged into many colour-neutral systems. Yet most experimentally established hadrons belong to the familiar families built from 3 quarks, or from 1 quark and 1 antiquark. Those patterns worked so well that they became the standard language of the subject. To see why tetraquarks cause such a disturbance, we now need to look at that older language more closely. We need to understand how baryons and mesons organised a bewildering collection of particles, why the quark model brought order to what once looked like a chaotic list, and how a rule that was never truly absolute came to feel almost unbreakable. By the middle of the 20th century, particle physics had developed a problem that looked less like a shortage of knowledge and more like an overflowing cupboard. New particles were appearing faster than anyone could comfortably organise them. Some were found in cosmic rays, where high-energy particles from space collided with atoms in the atmosphere. Others emerged from the growing number of particle accelerators, where physicists learned to produce energetic collisions under controlled conditions. Each discovery brought new measurements, new decay patterns, and usually a new name. Before long, the list had become so crowded that even specialists could be forgiven for wondering whether nature had developed an enthusiasm for unnecessary paperwork. At first, the proton, neutron and electron had seemed enough to describe the basic structure of ordinary matter. Protons and neutrons formed the nucleus, electrons occupied the space around it, and atoms combined into everything from hydrogen gas to kitchen tables. It was a beautifully economical picture. Then experiments began revealing unstable particles that did not belong to this familiar trio. There were pions, kaons, lambda particles, sigma particles, delta particles, and many others. Some existed for only a tiny fraction of a second. Others travelled surprisingly far before decaying. They carried different electric charges, different masses, and different patterns of behaviour. The growing collection became known as the particle zoo. It was a useful phrase because the situation really did resemble a zoo whose labels had been written before anyone had worked out which animals were related. Some particles looked similar but had different masses. Some decayed quickly through the strong interaction, while others with apparently similar properties survived much longer. A few behaved as though they followed hidden rules that physicists had not yet identified. Nature was providing the exhibits, but it had neglected to include the guidebook. The first major step toward order came from separating particles into broad families according to the forces they experienced. Electrons and neutrinos belonged to a group now called leptons. They did not participate in the strong interaction. Protons, neutrons, pions, kaons, and many of the other newly discovered particles did. These strongly interacting particles were called hadrons. The word hadron comes from a Greek word meaning thick or strong. It was chosen because these particles responded to the strong interaction. The term did not originally say anything about what hadrons were made of. It simply grouped them by their behaviour. A proton was a hadron, a pion was a hadron, a neutron was a hadron. The label was useful, but it did not yet explain why so many hadrons existed, or why they formed such noticeable patterns. Within the hadrons, physicists recognized two main categories. The heavier family was called baryons. The name came from a word meaning heavy, although not every baryon is heavier than every meson. Scientific names often preserve the history of an idea even after the idea has become more complicated. Protons and neutrons were baryons, along with many unstable relatives. The second family was called mesons, from a word meaning middle. Early mesons appeared to have masses between those of electrons and protons, though later discoveries made the name less literal. The distinction between baryons and mesons was not based only on mass. They differed in their quantum properties and in how they behaved during reactions. Baryons carried a property called baryon number. Ordinary baryons had a baryon number of 1. Antibaryons had a baryon number of -1. Mesons had a baryon number of 0. This accounting rule helped physicists understand which reactions were allowed and which appeared never to happen. A proton, for example, does not simply decay into light particles under normal conditions. Its baryon number seems to be conserved. If a baryon is created or destroyed in an ordinary reaction, the total baryon number before and after the event must remain balanced. This rule became one of the organizing principles of particle physics. It did not explain the internal structure of baryons, but it revealed that they belonged to a distinct family. Mesons followed a different pattern. They could be created and destroyed without changing the total baryon number because they carried none. Many mesons were extremely short-lived. They formed in energetic collisions and quickly decayed into lighter particles. Their brief existence did not make them unimportant. Mesons played a major role in the early attempt to explain the force holding protons and neutrons together inside atomic nuclei. In the 1930s, the physicist Hideki Yukawa proposed that the nuclear force might be carried by a new particle. His reasoning was based on the limited range of the force. Electromagnetism can act across enormous distances, but the force binding the nucleus works mainly over distances comparable to the size of the nucleus itself. Yukawa suggested that a particle with a certain mass could carry such a short-range interaction. The particle later identified with this role was the pion, a kind of meson. This was an important success, but it also added to the particle list. The more experiments improved, the more hadrons appeared. Some differed only in electric charge. Others formed groups with closely related masses and decay properties. It began to look as though the particles were not random. There was an underlying pattern, but the pattern was hidden behind a large number of names. One clue came from a property called strangeness. Certain particles were produced quickly in strong interactions, but decayed much more slowly than expected. They appeared in pairs, as though some hidden quantity had to balance during their creation. The physicists who studied them introduced the idea of strangeness as a bookkeeping property. The strong interaction seemed to conserve strangeness, while the weak interaction could change it. This explained why strange particles could be created easily, yet survive longer than similar particles before decaying. The name strangeness was not an attempt at drama. The particles genuinely seemed strange at the time. A kaon might be produced in a strong collision, suggesting that it should also decay rapidly through the strong interaction. Instead, it lived much longer because its decay required the weak interaction. Once strangeness was treated as a conserved quantity in strong processes, the behaviour made sense. More patterns followed. Hadrons could be arranged according to electric charge, strangeness, spin, and mass. In the early 1960s, Murray Gell-Mann and Yuval Neeman independently developed a classification system based on mathematical symmetry. Gell-Mann called it the Eightfold Way, borrowing the name from Buddhist teaching. The phrase was memorable, though the particles themselves were not being asked to seek enlightenment. The Eightfold Way arranged hadrons into groups. Mesons formed certain patterns, while baryons formed others. When the particles were plotted according to their properties, empty places appeared in the arrangements. These gaps were not merely untidy spaces. They suggested that undiscovered particles should exist with particular charges, masses, and quantum properties. One of the most famous predictions involved a baryon called the omega minus. The symmetry pattern required a particle with properties unlike those of the already known baryons. When the omega minus was discovered with the expected characteristics, it gave strong support to the classification system. The particle zoo was beginning to look less like a random collection, and more like a set of families built from a smaller number of underlying ingredients. This was the setting in which the quark model appeared. Gell-Mann and Zweig independently proposed that hadrons were composed of more fundamental objects. Gell-Mann called them quarks, while Zweig used the name aces. The word quark eventually became standard. The earliest version of the model used 3 quark flavors called up, down, and strange. Their combinations explained the patterns seen in the Eightfold Way. Baryons could be described as arrangements of 3 quarks. Mesons could be described as arrangements of 1 quark and 1 antiquark. Suddenly, many hadrons that had seemed independent could be understood as different combinations of the same small set of components. A proton contained 2 up quarks and 1 down quark. A neutron contained 1 up quark and 2 down quarks. Other baryons replaced one or more of these with strange quarks. Their electric charges and other properties followed from the quarks inside them. Mesons were built by pairing a quark with an antiquark. Different flavors produced different mesons, while different arrangements of spin and internal energy produced additional states. It was a remarkable simplification. Instead of treating every hadron as a separate elementary particle, physicists could describe the entire collection using a few quark ingredients and a set of combination rules. It was like discovering that a library containing thousands of words had been written from a small alphabet. The words were still numerous, but they no longer seemed unrelated. The model also explained why baryons and mesons formed different families. 3 quarks produced a baryon number of 1. A quark and antiquark pair produced a baryon number of 0. Antibaryons could be built from 3 antiquarks. The old classification rules were not discarded. They were understood as consequences of a deeper structure. As more quark flavors were discovered, the rulebook expanded. Charm, bottom, and top joined up, down, and strange. The top quark decayed too quickly to form hadrons, but the other 5 flavors produced a large range of mesons and baryons. A charm quark paired with an anti-up quark could form one type of meson. A charm quark paired with its own antiquark could form a family known as charmonium. Bottom quarks produced corresponding families. The old rulebook therefore became simple to state. A meson consisted of 1 quark and 1 antiquark. A baryon consisted of 3 quarks. An antibaryon consisted of 3 antiquarks. These combinations had to be neutral in color charge, even though they could carry electric charge. The rule fitted an enormous number of observations and gave physicists a clear way to classify new particles. There was a subtle problem, however. The rulebook described what had been seen most often. It did not necessarily describe everything the strong interaction could build. To understand this distinction, imagine that every house in a town has either one floor or two floors. After examining hundreds of houses, someone might write a local guide saying that houses come in one floor and two floor varieties. The statement would describe the town perfectly, but it would not prove that a 3-floor house was forbidden by architecture. It might simply mean that no one had built one yet, or that 3-floor houses were difficult to construct on the available ground. The quark model worked in a similar way. Mesons and baryons were the common, stable or resonant forms produced by the strong interaction. Yet the underlying rules of colour charge did not limit neutral combinations only to 2 or 3 constituents. More complicated arrangements could also produce an overall colour neutral object. 2 quarks and 2 antiquarks could, in principle, form a neutral combination. 4 quarks and 1 antiquark could do the same. Gluons might form bound states of their own. A quark and antiquark pair could combine with excited gluonic fields. The mathematics allowed a much richer collection of hadrons than the old rulebook usually displayed. Physicists were aware of these possibilities from the early days of the quark model. The idea of a 4-quark state was not invented only after experiments began finding unusual particles. Researchers discussed multi-quark arrangements and tried to understand whether they would be stable enough to observe. The difficulty was not showing that the theory permitted them. The difficulty was showing that nature formed a distinct particle, rather than a temporary overlap of ordinary hadrons. A system containing 2 quarks and 2 antiquarks can always be rearranged on paper into 2 quark and antiquark pairs. Each pair could form an ordinary meson. If the combined energy is high enough, the system may simply fall apart into those 2 mesons. For a genuine tetraquark state to be identifiable, the 4-constituent arrangement must create a recognizable resonance or bound state with properties that cannot be reduced to an accidental encounter. This made the search difficult. Suppose 2 mesons are produced close together and interact briefly. Their combined behavior might create an enhancement in experimental data. That enhancement could resemble a new particle. Researchers would then need to determine whether they had found a real 4-quark state, a molecule made from 2 mesons, a conventional meson affected by nearby decay thresholds, or merely a statistical fluctuation. The old hadron rulebook remained successful partly because the exotic possibilities were hard to distinguish. Ordinary mesons and baryons were clear, abundant, and well organized. More complicated states, if they existed, were unstable and often hidden among many conventional processes. The absence of obvious evidence encouraged a cautious attitude. There was also a theoretical challenge. Quantum chromodynamics is difficult to calculate at the energy scales where quarks become confined inside hadrons. Physicists know the theory, but extracting precise predictions for complex bound states can require enormous computational effort. Simple quark models offered useful approximations, yet a 4-body quantum system under the strong interaction was far more demanding than the familiar pair or trio. Even conventional hadrons were not always as simple as the rulebook made them sound. A meson described as 1 quark and 1 antiquark also contained gluons and temporary quark and antiquark pairs. A baryon described as 3 quarks contained a busy sea of additional activity. The labels identified the valence content that determined the particle's main quantum numbers. They did not provide a frozen inventory of everything inside. This meant that physicists had to be careful when using the word exotic. Every hadron contained complicated quantum fields. A tetraquark was not exotic merely because 4 quarks could be found somewhere in its internal fluctuations. Extra pairs appeared even inside ordinary hadrons. What mattered was whether the particle required a 4-constituent valence structure to explain its identity. Electric charge and flavour became especially useful clues. An ordinary meson has 1 quark and 1 antiquark. This limits the combinations of charge and flavour it can carry. If a particle appeared with quantum numbers impossible for a single pair, then a more complicated arrangement would be required. Such a state would be called manifestly exotic because its unusual nature could be read directly from its properties. Other particles were harder to classify. A state containing a charm quark and a charm antiquark might look like an excited charmonium meson. If its mass or decay behavior did not fit the expected charmonium pattern, it could be a tetraquark candidate. But conventional and exotic explanations might compete for years. The term candidate became important. Particle physicists did not want to declare a tetraquark every time an unusual bump appeared in a graph. A signal had to survive statistical testing, independent measurements, and theoretical examination. Some early claims disappeared when more data were collected. Others remained but changed interpretation. The old rulebook was therefore not destroyed by tetraquarks. It still describes the vast majority of known hadrons extremely well. Protons remain 3-quark baryons. Pions remain quark and antiquark mesons. The familiar categories continue to organize particle physics. What changed was the assumption that those categories were complete. A good scientific rule can be both useful and incomplete. Newtonian physics still describes falling objects, bridges, and planetary motion under ordinary conditions, even though relativity provides a deeper account. In the same way, the meson and baryon picture remains an essential first description of hadrons, even after more complex states have been established. The important difference is that the old rulebook once seemed to describe all the pages. Tetraquarks revealed that it described the most commonly opened pages. Beyond them was a larger volume in which the strong interaction could combine quarks in ways that were allowed but difficult to produce, difficult to detect, and even more difficult to interpret. Before that larger volume could be read, experiments needed to encounter particles that refused to sit neatly in the expected patterns. Some had the wrong masses for conventional mesons. Some decayed into unexpected products. Some carried electric charges that demanded more than one quark and one antiquark. Each irregularity was small on its own, but together they began to suggest that the old shelves were no longer enough. The first clues did not arrive with a label saying Tetraquark. They appeared as puzzling resonances, uncertain peaks, and particles that seemed to have all the correct paperwork for existence, but none of the correct paperwork for classification. That was when the tidy rulebook began to develop its first loose pages. The old rulebook had brought order to the particle zoo, but order in science is always provisional. A classification system can be remarkably successful without being complete, and a pattern can remain convincing until one stubborn observation refuses to fit inside it. For many years, the familiar hadron families seemed to account for almost everything experiments produced. A particle made from 3 quarks was placed among the baryons. A particle made from 1 quark and 1 antiquark was placed among the mesons. The shelves were crowded, but the labels appeared dependable. There had always been hints that the shelves might not be large enough. Some of the lighter mesons had masses and decay patterns that were difficult to explain using the simplest quark and antiquark picture. Theorists proposed that certain particles might contain 4 important quark constituents rather than 2. Other possibilities included tightly interacting pairs of ordinary mesons or mixtures of several configurations. These ideas were scientifically respectable, but the evidence was rarely decisive. The problem was not that 4-quark arrangements were forbidden. Quantum chromodynamics allowed color-neutral combinations containing more than the usual 2 or 3 valence constituents. The problem was deciding whether any measured signal truly required such a structure. A particle could behave unexpectedly because calculations were incomplete. It could be an ordinary meson in an unusual excited state. It could be affected by a nearby decay threshold. It could arise from 2 particles interacting briefly without forming a distinct new object. It could even be a statistical fluctuation, the experimental equivalent of seeing a face in the pattern on a curtain after staring at it for too long. Particle physicists, therefore, learned to be cautious. A strange bump in a graph was not immediately welcomed into the official particle family. It had to return in more data. It had to appear in other experiments. researchers had to test whether known particles and known processes could imitate it. The signal needed a mass, a width, characteristic decay patterns, and eventually enough information about its quantum properties to separate it from the background. This careful approach was essential because particle detectors do not display a new hadron directly. They record the particles that survive long enough to travel through layers of equipment. Unstable particles must be reconstructed from the tracks and energies of their decay products. Researchers combine those products mathematically and ask whether particular combinations repeatedly point back to the same mass. Imagine arriving in a room after a vase has fallen. You did not see the fall itself, but you can study the fragments. If several pieces fit together, you may reconstruct the shape of the vase. If the same kind of fragments appear after many similar events, you can become confident that the same type of object was present each time. Particle reconstruction works through a far more precise and complicated version of that reasoning, except the fragments may themselves decay before reaching the detector, leaving fragments of fragments and a very large amount of computing to be done before anyone is allowed a cup of tea. For decades, unusual hadron signals appeared and disappeared without producing a universally accepted tetraquark. Then, at the beginning of the 21st century, experiments studying particles containing charm quarks began to encounter a series of states that proved much harder to dismiss. Charm hadrons were already well established. A charm quark could pair with an antiquark to form a meson. When a charm quark paired with a charm antiquark, the resulting family was called charmonium. The name followed the same pattern used for positronium, a temporary system formed from an electron and a positron. Charmonium was valuable because its spectrum could be predicted with considerable success. Different arrangements of internal energy, spin, and motion produced a sequence of states, rather like notes available to a complicated quantum instrument. Many of those notes had been found where theory expected them. Their masses and decays fitted the conventional picture well enough that charmonium became one of the cleaner testing grounds for the strong interaction. It was not simple, but it was organized. Physicists knew which spaces in the spectrum were occupied, which remained available, and approximately what an undiscovered conventional state ought to look like. That confidence made the next discovery particularly noticeable. In 2003, the Bell experiment in Japan was studying the decays of particles called B-mesons. B-mesons contain a bottom quark or bottom antiquark and can decay through several complicated routes, producing lighter particles along the way. Bell operated at the KEKB accelerator, where electrons and positrons were collided to create large numbers of B-meson pairs. The experiment was not built solely to search for tetraquarks. It was designed to investigate many questions involving heavy quarks, matter, antimatter, and the weak interaction. Among millions of B-meson decays, the Bell researchers found a narrow signal in a combination containing a JPSI particle and two pions. The JPSI was already a famous charmonium state, made primarily from a charm quark and a charm antiquark. The new signal had a mass near 3,872 million electron volts. It became known as X3872. The letter X was a sign of uncertainty rather than excitement alone. In particle naming, letters often indicate categories, but the new state did not sit comfortably inside a familiar one. It was charmonium-like because it decayed into a final state containing a JPSI, yet it did not behave like an ordinary charmonium state expected at that mass. One of its most striking features was how narrow it appeared. In particle physics, width is related to lifetime. A very broad resonance usually decays extremely quickly through readily available processes. A narrow resonance survives slightly longer, though still for an interval far too short for human senses. At the mass of X3872, a conventional excited charmonium state might have been expected to decay through strong interactions into open charm mesons and therefore to have a more substantial width. Instead, the new particle was surprisingly narrow. Its mass was also extremely close to the combined mass of two particular charm mesons, called the neutral d meson and the neutral d star meson. This closeness immediately attracted attention. When a new state lies almost exactly at the threshold for forming two known particles, it may be related to those particles in an important way. A threshold is simply the minimum energy needed to produce a certain set of particles. Below that energy, the process cannot happen because there is not enough energy to provide their masses. Just above it, the process becomes possible. The behavior of a quantum system can change noticeably near such a boundary. Interactions among the particles may produce enhancements, bound states, or resonances that would not appear in the same way far from the threshold. The location of X3872 led to the suggestion that it might be a hadronic molecule formed mainly from a neutral d meson and a neutral d star meson. These two mesons could remain weakly bound through residual effects of the strong interaction, much as a proton and neutron bind inside a nucleus, even though each is already a complete colour-neutral hadron. Calling it a molecule did not mean that it resembled an ordinary chemical molecule in size or structure. Chemical molecules are held together through electromagnetic interactions among atoms. A hadronic molecule would be held through the leftover influence of the strong interaction between hadrons. Still, the analogy captured an important idea. The object might consist of two recognizable mesons staying near each other, rather than four quarks forming a compact cluster. Other researchers proposed a compact tetraquark. In that picture, the charm quark, charm antiquark, and two like constituents would form a single integrated hadron. Some suggested that two quarks might cluster into a diquark, while the two antiquarks formed an anti-diquark. The two clusters could then bind through the strong interaction. There were also proposals involving mixtures. X3872 might contain a conventional charmonium component blended with molecular and four-quark configurations. Quantum states are not required to respect the boundaries of our diagrams. If several arrangements share the same overall quantum properties, the physical particle may include contributions from more than one. This made X3872 both exciting and frustrating. It was clearly real. Other experiments confirmed it. Its properties were unusual, yet its existence alone did not provide a simple answer to its internal structure. The first major clue that something did not fit had arrived, but it was written in handwriting that no one could read with complete confidence. Further measurements deepened the puzzle. The particle decayed through routes involving combinations associated with different isospin behavior. Isospin is a quantum symmetry connected to the similarities between up and down quarks. In many strong interaction processes, this symmetry works very well. The decays of X3872 appeared to involve unexpectedly strong isospin violation, which was awkward for a simple conventional charmonium interpretation. Its quantum numbers were eventually determined to match a particular combination of spin, parity, and charge conjugation. These properties were consistent with several exotic models and made some conventional assignments implausible. Yet even with improved measurements, the debate did not collapse into a single agreed picture. X3872 became a lasting example of how a particle can be firmly established, while its identity remains unsettled. Then more unfamiliar states appeared. Experiments began reporting charmonium-like particles given names beginning with X, Y, and Z. The letters were used because these states did not fit comfortably into the established charmonium naming system. Some were produced in unexpected ways. Some decayed into final states containing charmonium, but had masses inconsistent with available conventional levels. Some were too narrow, others were too broad. Several sat near thresholds involving pairs of known heavy mesons. One important example was with 4260, observed in the middle of the first decade of the century. It appeared in a process involving a J-psi and two pions, yet it did not match the expected behavior of ordinary charmonium at that energy. Its relationship with open charm channels was also unusual. The state added another loose page to the old rulebook, though it was not a direct proof of a tetraquark. The X and Y particles could still, at least in principle, be conventional quark and antiquark states with unexpected properties. A charm quark paired with a charm antiquark carries no net electric charge, so a neutral charmonium-like signal did not automatically require extra quarks. Its mass and decays might be puzzling, but the ordinary two-constituent explanation had not been logically excluded. A charged charmonium-like state would be different. A charm quark has a positive electric charge of 2/3 of the proton charge. A charm antiquark has a negative charge of the same size. Together they are electrically neutral. Any particle containing a charm quark and charm antiquark as its only valence constituents must therefore have no net electric charge. If an object decayed into a charmonium state while also carrying electric charge, it could not be made from only that charm pair. Additional light quark content would be required to provide the charge. This would make the state manifestly exotic. The evidence would no longer depend only on a mass that seemed inconvenient or a decay that looked unusual. Its electric charge would demand more constituents than an ordinary meson contained. In 2007, the Bell experiment reported just such a clue. Researchers studying B-meson decays found a resonance-like structure in a combination of a charged pion and an excited charmonium state called Passif prime. The new structure was named Z4430. The decay products mattered enormously. The PSI prime contained a charm quark and charm antiquark. The charged pion required a light quark and light antiquark combination carrying electric charge. For the parent particle to produce these components, while itself carrying charge, its minimal valence content had to include at least 4 quark constituents. A conventional charmonium meson could not do the job. It was the kind of signal Tetraquark hunters had wanted. Yet physics did not immediately place a gold frame around the graph. The decay process was complicated. The B-meson also produced a kaon, and combinations involving the kaon and pion could form known resonances. Those resonances might create patterns that reflected into the distribution being studied. A feature in one combination of particles can sometimes appear because of dynamics occurring in another combination. The experimental analysis had to separate a genuine new resonance from these reflections. Bell examined the data and concluded that the charge structure was significant. The result attracted enormous interest because it provided a possible manifest tetraquark. Its minimal quark content could be described using a charm quark, a charm antiquark, and a light quark and antiquark carrying the necessary charge. Another major experiment, Babar, then studied related data and did not find significant evidence for the same state. The Babar researchers showed that known resonances involving the kaon and pion could account for the distributions they observed. This created a scientific disagreement, though not the dramatic sort sometimes imagined in films. No one overturned a table or challenged a rival collaboration to settle the issue beside the accelerator. Instead, researchers questioned models, compared analysis methods, and waited for more data. Disagreement of this kind is not a weakness in experimental science. It is part of the method. Complex data can support different interpretations, especially when signals are limited and backgrounds are difficult. Independent experiments are expected to test one another. A result becomes stronger when it survives serious attempts to explain it away. Bell later performed a more detailed analysis and continued to find evidence for Z4430. The collaboration also investigated its possible spin and parity. The case improved, but uncertainty remained. What the field needed was a larger data sample and an analysis capable of tracking not merely a bump in the mass distribution, but the characteristic behavior of a true resonance. That opportunity came from the Large Hadron Collider Beauty Experiment, known as LHCb. The detector was designed to study particles containing bottom and charm quarks. Proton collisions at the Large Hadron Collider produced enormous numbers of heavy hadrons, giving LHCb a rich collection of B-meson decays. In 2014, LHCb reported a detailed analysis of the decay channel associated with Z4430. The collaboration had a much larger sample than the original Bell study. Researchers performed a multi-dimensional analysis accounting for the known kaon and pion resonances and the angular relationships among the decay products. The data could not be adequately explained using the known kaon and pion structures alone. A component corresponding to Z4430 was required with very high statistical significance. More importantly, LHCb studied how the particle's amplitude changed across the mass region. A genuine resonance does not merely create a hill in the number of events, its quantum amplitude changes in a characteristic way as the energy passes through the resonance. Both the size and the phase of the amplitude evolve. This behavior can be represented through a looping pattern in a particular kind of plot. The measured behavior of Z4430 followed the pattern expected from a real resonant state. The signal was no longer merely an unexplained excess. It behaved like a particle. This confirmation mattered because the state was electrically charged and decayed into charmonium. Its minimal quark content could not be reduced to a single quark and antiquark pair. At least 4 constituents were needed. Whether those constituents formed a compact tetraquark, a hadronic molecule, or another strongly interacting arrangement remained open. But the old 2-constituent meson explanation was not sufficient. The word tetraquark began to move from theoretical possibility toward experimental reality. It had not happened through one perfectly clear announcement. The path had been gradual. There were puzzling light mesons. There was X3872, narrow and almost exactly aligned with the charm meson threshold. There were further X and Y states that crowded the charmonium region without fitting the expected spectrum. Then a charged Z state appeared, was questioned, re-examined, and eventually shown to have the resonant behavior of a genuine particle. The process illustrates how discoveries often unfold in particle physics. A new idea does not always arrive as a single undeniable flash. It may begin as a mismatch. A predicted state is missing while an unpredicted one appears. A mass lies too close to a threshold. A decay violates expectations. A charged object emerges where a neutral conventional state should have been. Each clue can be explained away separately for a time. Perhaps the model needs adjustment. Perhaps the data contain an overlooked background. Perhaps the detector has produced an illusion. Scientists test each possibility because extraordinary interpretations should not be preferred merely for being interesting. Eventually, however, the irregularities can form a pattern of their own. The question changes. Researchers stop asking whether one awkward particle might have been misunderstood and begin asking why an entire family of awkward particles has appeared. The collection of X, Y, and Z states suggested that heavy quarks were participating in arrangements beyond ordinary charmonium. Their closeness to meson thresholds hinted at hadronic molecules. Their electric charges sometimes demanded additional light quarks. Their production and decay rates suggested compact components in at least some cases. No single model explained every state. This was an important lesson. The term tetraquark might not describe one rigid architecture. Four-quark states could form in more than one way. Some might be loose pairs of mesons. Some might be tightly bound clusters. Some might continually shift between those descriptions. The strong interaction could produce a spectrum of structures, rather than one new box to place beside mesons and baryons. The early clues therefore did more than reveal several unusual particles. They changed the type of question physicists were asking. The old rulebook had focused on counting the minimum valence constituents and assigning each particle to a familiar family. The new evidence demanded attention to internal organization, thresholds, clustering, and the possibility that the same quark content could create very different physical objects. A proton is not interchangeable with 3 free quarks. A conventional meson is not merely any place where a quark and antiquark happen to meet. In the same way, a tetraquark is not defined only by counting 4 names on an ingredient list. The interactions among those constituents determine whether they form 1 compact state, 2 bound hadrons, or a resonance existing briefly between several possibilities. That distinction is where the subject becomes more precise. The phrase four-quark particle sounds straightforward, but every word needs care. The 4 constituents are not directly observed. They do not occupy fixed positions. Additional quark pairs and gluons are always present in the full quantum state. Even the word particle must include objects that survive for only a minute fraction of a second before becoming something else. The evidence had shown that the old categories were incomplete. To understand what had taken their place, physicists now had to decide what the name tetraquark really meant. What made such a state different from 2 ordinary mesons passing close together, and how 4 quark constituents could belong to 1 particle without sitting inside it like 4 beads in a box. The first clues had shown that some particles could not be understood comfortably within the old arrangement of ordinary mesons and baryons. A charged state containing a charm quark and a charm antiquark required additional quark content. Other states appeared close to pairs of known mesons, and behaved as though those mesons were connected in some unusual way. The evidence pointed towards systems involving 4 quark constituents, but that still left a deceptively simple question. What exactly makes such a system a tetraquark? The easiest answer is that a tetraquark is a hadron, with a minimum constituent content of 2 quarks and 2 antiquarks. That statement is correct, but it is only the front door of the explanation. Walking through it reveals several rooms, some connected by corridors that physicists are still trying to map. The word tetra tells us that 4 important quark constituents are involved. The word quark tells us what kind of constituents they are, yet a tetraquark is not simply any place where 4 quarks happen to be present. Ordinary protons and mesons already contain temporary quark and antiquark pairs within their restless quantum interiors. A proton is usually described through 3 valence quarks, but it also contains gluons and a sea of additional quarks and antiquarks. If we counted every brief fluctuation, even an ordinary proton would appear to contain far more than 3 quarks. What identifies the proton is not a frozen inventory taken at one instant. Its identity comes from the valence arrangement that determines its main properties, along with the complete quantum state created by the strong interaction. In the same way, a tetraquark is not defined by catching 4 quarks in the same microscopic neighbourhood. Its observable properties require a 4-constituent description at the valence level, or its behaviour is dominated by a structure built from 2 quarks and 2 antiquarks. The word valence is borrowed from chemistry, where it describes how atoms connect with one another. In particle physics, valence quarks are the constituents that account for the main flavour, electric charge, and other defining properties of a hadron. The proton has 2 up valence quarks and 1 down valence quark. Additional pairs inside it may appear and disappear, but they do not change the fact that the proton behaves as a baryon with that basic 3-quark identity. A tetraquark follows the same idea. Suppose a particle contains a charm quark and a charm antiquark. Those 2 alone would form an electrically neutral charmonium meson. If the observed particle carries electric charge, more constituents must be present. A light quark and a light antiquark can provide that charge. The minimum description then contains 4 valence constituents. No ordinary quark and antiquark meson can reproduce the same combination of flavour and charge. Such a particle is called manifestly exotic. Its exotic nature is visible directly from its quantum properties. Physicists do not need to rely entirely on an awkward mass or an unexpected lifetime. The particle carries a kind of identification that the conventional meson rulebook cannot issue. Other tetraquark candidates are less obvious. A neutral particle containing a charm quark and charm antiquark could still be an ordinary charmonium state. If two light constituents are also important, the object might instead be a tetraquark. Both possibilities can produce the same total electric charge and some of the same other quantum properties. Researchers then have to study the particle in greater detail, examining its mass, production rate, decay channels, lifetime, and relationship to nearby hadron thresholds. This is where the meaning of tetraquark becomes more subtle. There are at least two broad ways to imagine four constituents forming one observable state. The first is a compact arrangement. In this picture, the two quarks and two antiquarks occupy one strongly connected region. None of the ordinary meson pairings provides a complete description on its own. The four constituents participate together in a single, tightly organized hadron. The second possibility is a hadronic molecule. Here, the quarks may already be grouped into two ordinary mesons. Each meson is color neutral and recognizable as a conventional hadron. The two mesons then remain bound or resonantly connected through the leftover influence of the strong interaction. The resulting object still has a minimum quark content of two quarks and two antiquarks, but its internal organization resembles two particles forming a larger structure. The comparison with an ordinary molecule is useful if handled gently. A water molecule contains atoms that retain much of their individual identity while sharing electrons through the electromagnetic interaction. A hadronic molecule would contain hadrons that retain much of their identity while interacting through residual strong forces. The scales and forces are completely different, but both involve recognizable smaller units forming a larger bound system. A hadronic molecule is not a molecule made from tiny atoms. It does not contain a miniature bottle, and no one should attempt to pour it. It is a quantum object formed from hadrons rather than atoms. The distinction between compact tetraquarks and hadronic molecules sounds clear when stated in words. One is a tightly integrated four-constituent state. The other is a loosely bound pair of mesons. Nature, however, does not always separate the possibilities so politely. A physical particle may contain several arrangements at once. A compact four-quark component can mix with two meson components if they share the same overall quantum properties. The object detected in an experiment may therefore be partly compact and partly molecular. The balance can depend on its energy and on how it was produced. One experiment may be more sensitive to one component, while another process reveals a different aspect of the same state. This is not indecision on the part of the particle. Quantum systems are simply not required to choose one classical picture. An electron in an atom does not travel around the nucleus along one hidden little orbit. It occupies a quantum state that may be described through a spread of possibilities. A tetraquark can likewise be a combination of configurations rather than a single, permanent arrangement. Imagine a person who spends part of the week working in an office and part working at home. Asking whether that person is an office worker or a home worker may not have one exclusive answer. Both descriptions contribute to the complete routine. The analogy is not exact, but it captures the difficulty of demanding one rigid label from a quantum state capable of mixing. This creates a difference in how the word tetraquark is used. In a broad sense, any distinct hadronic state with a minimum content of two quarks and two antiquarks may be called a tetraquark. Under this definition, a hadronic molecule made from two mesons belongs to the tetraquark family because the complete object still requires four valence constituents. In a narrower sense, some physicists reserve the word tetraquark for compact four-quark states and use hadronic molecule as a separate category. Under that convention, both are exotic hadrons, but only the tightly bound arrangement receives the tetraquark label. Neither usage changes the experimental facts. It reflects a difference in classification. When reading about a tetraquark, it is therefore helpful to notice whether the writer means any exotic four-constituent hadron or specifically a compact object. Particle physics already contains enough mystery without two people using the same word for slightly different filing systems. There is another possibility known as the diquark and antiquark picture. A diquark is a correlated pair of quarks. It is not usually an isolated particle because it carries colour charge, but two quarks inside a hadron may interact strongly enough to behave like a cluster. The two antiquarks can form a corresponding anti-diquark cluster. The diquark and anti-diquark may then bind together into an overall colour-neutral tetraquark. This picture lies within the compact family, though the strength and size of the clusters can vary. One should not imagine two perfectly solid lumps connected by a string. The clusters are quantum correlations, not tiny stones. Still, the idea can simplify the four-body problem by replacing four equally independent constituents with two strongly related pairs. Quarks can also pair with antiquarks inside the same tetraquark. If each quark forms a dominant relationship with one antiquark, the structure begins to resemble two mesons. The internal colour arrangement can change through gluon exchange, so the particle may continually move among different pairings. What looks like a disquark arrangement in one useful description may be rewritten in terms of meson-like pairings in another. This is one reason drawings of tetraquarks must be treated as illustrations rather than photographs. A diagram showing four coloured circles connected by lines can help the eye, but the real particle is not sitting still in that pattern. Its constituents are quantum fields. Gluons are exchanged, colour relationships change, additional quark and antiquark pairs contribute. The diagram selects one aspect of a much richer state. A tetraquark must be colour neutral as a whole. Quarks carry colour charge, and antiquarks carry corresponding anti-colour charge. The combined system must hide all exposed colour from the outside world. There are several mathematical ways for four constituents to achieve this neutrality. One arrangement groups a quark with an antiquark into one colour neutral pair, and the remaining quark with the remaining antiquark into another. This resembles two mesons. Another arrangement allows the two quarks to form a coloured diquark, while the two antiquarks form the balancing coloured anti-diquark. Neither cluster is neutral alone, but the complete tetraquark is neutral. The different colour arrangements can mix. The strong interaction does not always preserve the neat pairings used in a drawing. Gluons can rearrange the colour connections, allowing the system to move between configurations. The identity of the particle belongs to the complete colour-neutral state, not to one line pattern chosen for a textbook illustration. A useful question now appears. If two mesons move close together, does that automatically create a tetraquark? The answer is no. Particles frequently pass near one another and interact without forming a new state. Two mesons may scatter, exchange energy, and move apart. During their encounter, the combined system contains two quarks and two antiquarks, but this temporary meeting is not necessarily a tetraquark. For physicists to identify a distinct particle, the interaction must produce a repeatable structure. The system may form a bound state with a mass below the energy needed for the two mesons to separate freely, or it may form a resonance above that threshold, delaying the scattering and creating a characteristic pattern in the experimental data. A bound state is stable against falling apart through a particular route, because its total energy is lower than the energy of the separated products. It may still decay through other interactions, but it cannot simply divide through that one channel without receiving additional energy. A resonance is less securely held. It exists briefly before decaying, yet it behaves as a distinct quantum state during that interval. A familiar analogy is a bell. Air molecules strike and scatter from a metal bell all the time, but when the bell vibrates at one of its natural frequencies, the response becomes organised and persistent. The sound reveals a characteristic mode of the whole object. A particle resonance is not a sound, but the analogy captures the idea of a system responding strongly at a particular energy. In experiments, a resonance often appears as an increase in the number of events near a particular reconstructed mass. But a bump alone is not always enough. Threshold effects and reflections from other processes can also create bumps. Researchers examine how the full quantum amplitude changes across the region, including both its strength and its phase. A true resonance produces characteristic behavior that a simple accidental enhancement may not. This distinction matters enormously for tetraquarks. Four constituents can participate in an event without forming a new particle. Two mesons can attract each other without producing a stable or resonant state. A tetraquark must be more than a convenient way of counting the quarks present after a collision. It must correspond to a distinct feature of the strong interaction. The lifetime of such a feature may be astonishingly short. Many tetraquark candidates decay through the strong interaction almost as soon as they form. Their lifetimes are measured through their decay widths rather than with an ordinary clock. A broad state decays more rapidly. A narrow state survives somewhat longer. Even the longer-lived examples exist for far less than a billionth of a second. Yet duration is not the measure of reality. A particle can be real if it forms consistently, carries definite quantum properties, and produces reproducible decay behavior. Lightning does not need to last all afternoon to count as weather. A tetraquark also has properties belonging to the whole object. It has a total mass, electric charge, spin, parity, and sometimes other quantum labels connected to flavor. These are not assigned separately and then placed in a bag. The constituent properties combine with their motion and interactions to produce the observable state. The mass is especially revealing because it is not merely the sum of the quark masses. Much of a hadron mass comes from the energy of motion, gluon fields, and strong interactions. Binding can lower the total energy, while internal excitation can raise it. Two tetraquarks with the same quark flavors may therefore have different masses if their spins, color arrangements, or internal motion differ. This means there can be families of tetraquarks, just as there are families of ordinary mesons. The same basic constituent content may support several energy levels and quantum configurations. Some will be too broad to distinguish easily. Others may be narrow enough to appear as clear peaks. Certain combinations may not bind at all. The flavors involved strongly affect the outcome. Light quarks move rapidly and participate in complicated quantum fluctuations. Heavy charm and bottom quarks provide larger masses and may create more stable arrangements. Two heavy quarks can attract in ways that make certain tetraquarks especially interesting. Fully heavy states containing only charm quarks and charm antiquarks, or only bottom-related constituents, offer another testing ground because all four components are heavy. A famous example involving two charm quarks and two light antiquarks showed how unusual flavor content can strengthen the classification. Such a state carries 2 units of charm without containing charm antiquarks to cancel them. An ordinary meson cannot hold 2 charm quarks, because a meson contains only 1 quark and 1 antiquark. The particle therefore demands a 4-constituent minimum arrangement. Some of these states lie close to the thresholds of 2 ordinary mesons. If their mass is just below such a threshold, they may be unusually narrow because the easier strong decay route is unavailable. A small difference in mass can therefore make a great difference in lifetime. Particle physics is sometimes decided by energy margins so tiny that an everyday accountant would refuse to print them, yet nature keeps every decimal place. A tetraquark can decay by rearranging its constituents. A quark from one internal pairing may join an antiquark from another, producing 2 ordinary mesons. No quark needs to vanish for this to happen. The color connections simply reorganize, and the original 4-constituent state becomes 2 separate color-neutral particles. Other decays involve quark and antiquark annihilation or transformations through the weak interaction. The available routes depend on flavor, mass, spin, and conservation rules. By measuring which decays occur often and which are suppressed, physicists gain clues about the internal structure. A compact tetraquark may be produced differently from a large molecular state. Compact objects can form efficiently in energetic collisions where quarks are created close together. A very loose molecule may be expected to form more readily when its component mesons emerge with nearly matching velocities and can remain near each other. Yet production data are difficult to interpret because the collision environment is complicated. A molecular state may contain a small compact component that helps it form. A compact state may spend much of its time in meson-like configurations. Once again, nature refuses to remain inside the simplest boxes. The size of the object can also differ. A tightly bound tetraquark might have a radius similar to that of an ordinary hadron. A weakly bound molecule could be much larger, with its meson components separated by a comparatively wide distance. Large is still microscopic, of course. No molecular tetraquark is likely to block a doorway, but relative to other hadrons, the difference may be substantial. Directly measuring such a size is extremely difficult because the particle decays so quickly. Researchers infer structure from scattering properties, binding energy, production rates, and decay patterns. Each measurement contributes one part of the picture, rather like trying to determine the shape of an object inside a sealed box by listening to how it rattles. This explains why physicists may agree that a tetraquark candidate exists, while disagreeing about what kind of tetraquark it is. Existence and internal structure are separate questions. The signal may be beyond reasonable doubt, but the most useful internal description may remain uncertain. The charged Z states provide a good example. Their charge and hidden charm content establish that more than a charm quark and charm antiquark are required. They are exotic four-constituent states in the broad sense. But whether their constituents form compact d-quark structures, meson molecules, or strongly mixed states is still a deeper problem. The particle known as X3872 presents the opposite difficulty. Its mass lies extraordinarily close to a neutral charm meson threshold, strongly suggesting a molecular component. At the same time, its production in energetic collisions and some of its decay behavior may indicate a more compact component. It may be most accurate to describe it as a mixed state rather than forcing it to choose one identity. This does not weaken the concept of a tetraquark. It enriches it. The discovery was never simply that quarks can be counted to 4. The deeper discovery was that the strong interaction supports structures beyond the familiar meson and baryon patterns, and that those structures may occupy a range between compact hadrons and loosely bound hadronic molecules. Matter therefore has more ways of organising itself than the old rulebook first suggested. A tetraquark is one of those ways. It is a colour-neutral hadronic state, whose defining quantum structure involves 2 quarks and 2 antiquarks. It may be compact, molecular, clustered, mixed, or something that our present models only partly capture. It exists not as 4 static beads, but as a complete quantum pattern, held and reshaped by the strong interaction. The name tells us how many valence constituents are required. It does not tell us how far apart they are, which pairings dominate, how tightly they bind, or why one combination becomes a clear particle, while another immediately dissolves into 2 mesons. Those questions depend on the detailed behavior of color charge, gluon exchange, quark masses, thresholds, and quantum symmetry. To understand why 4 constituents sometimes remain together long enough to form a recognizable state, we now have to move from definition to mechanism. The tetraquark has been named, but the strong interaction still has to explain how it performs the difficult task of holding 4 restless quantum objects inside one temporary piece of matter. Once 4 quark constituents have gathered into the same quantum system, their continued existence is not guaranteed. The strong interaction may permit the arrangement, but permission is not the same as stability. 4 people are permitted to stand beneath one umbrella, yet whether they remain there depends on the size of the umbrella, the weather, and whether anyone has remembered that there is a perfectly dry cafe across the street. Quarks face a similar problem, though their disagreement is governed by colour charge rather than rain. The strong interaction binds quarks through the exchange of gluons. Inside an ordinary meson, a quark and an antiquark form an overall colour-neutral combination. Inside a baryon, 3 quarks combine their colours so that the complete particle is neutral. A tetraquark must also be colour neutral, but 4 constituents can reach that condition in several ways. The details of those colour arrangements help determine whether the system remains together, rearranges into two mesons or disappears into other particles almost as soon as it forms. It is tempting to imagine the strong force as a general-purpose glue that binds any nearby quarks into one permanent object. The name gluon certainly encourages that impression, but gluons are not microscopic drops of adhesive, and the strong interaction does not treat every combination equally. Some colour arrangements are attractive, others are less attractive or effectively repulsive. The amount of attraction also depends on the quark flavours, their spins, their motion, and the distance between them. Even when attraction exists, it must compete with the restless quantum motion of the constituents. A particle cannot be built merely by placing quarks near one another and asking them to remain still. Quantum objects do not sit quietly at exact positions. Confining them to a small region increases the uncertainty in their motion, and therefore increases their kinetic energy. A tightly packed tetraquark may gain binding energy from attraction, but it also pays an energy cost for squeezing four constituents into a confined space. A stable or resonant state appears only when the total balance works. The attractive interactions must be strong enough to produce a recognizable energy level. If the energy of the combined system is lower than the energy of the easiest available decay products, the tetraquark may be unable to fall apart through the strong interaction. If it lies slightly above that level, it may survive only briefly as a resonance. If it lies far above several open decay routes, it may dissolve so rapidly that distinguishing it from ordinary particle scattering becomes extremely difficult. The energy separating a possible tetraquark from its most natural decay products is often discussed in relation to a threshold. Suppose the four constituents can rearrange into two ordinary mesons. Those two mesons have a combined minimum energy determined mainly by their masses. If the tetraquark lies below that threshold, it does not possess enough energy to separate into those particular mesons. It is bound against that decay route. If its energy lies above the threshold, the two mesons can be produced. The tetraquark may still form a resonance, but the door to escape is open. Whether it leaves immediately depends on how easily the internal configuration can rearrange into the final particles. An everyday comparison might involve a marble resting in a shallow bowl. If the marble lacks enough energy to climb over the rim, it remains trapped. If it receives slightly more energy, it can escape, though it may circle the bowl for a while before finding the way out. If the rim is almost non-existent, the marble rolls away without establishing much of a resonance at all. A tetraquark energy level behaves nothing like a literal marble, but the image captures why the position of a state relative to its thresholds matters so much. For a compact tetraquark, one proposed binding mechanism begins with a correlated pair of quarks called a diquark. Two quarks cannot form an ordinary colour-neutral particle by themselves. Each carries colour charge, and their combination still carries colour. Yet certain ways of combining their colours are attractive. The most favourable of these can encourage the quarks to remain close and behave as a correlated pair. The two antiquarks may form a corresponding anti-diquark. It carries the matching colour needed to neutralise the diquark. Neither cluster could exist freely, but together they can produce an overall colour-neutral state. The tetraquark then resembles a coloured diquark bound to a coloured anti-diquark. The word cluster can make these objects sound more rigid than they are. A diquark is not a tiny sealed particle with two quarks locked inside. It is a strong correlation within the complete hadron. The quarks may spend much of their time arranged in a way that makes the pair useful as a single unit, but gluons continue to move colour among all four constituents. The diquark description is a model of the dominant organisation, not a photograph of permanent boundaries. Quarks within a diquark must also obey the quantum rules applying to identical fermions. If two identical quarks are involved, the combined arrangement of their colour, spin, flavour and motion must satisfy the exclusion principle. Changing one property can alter which choices are allowed for the others. A colour arrangement that provides attraction may require a particular spin state. A different flavour combination may permit another configuration. This creates preferred diquarks. Some pairs are more strongly correlated because their colour and spin arrangement lowers the energy. Light up and down quarks can form particularly favourable combinations under certain conditions. Heavy quarks can also form attractive pairs, and their large masses may help the complete system remain bound. Heavy quarks move differently from light quarks inside a hadron. They still obey quantum mechanics and remain far from motionless, but their greater mass generally reduces the kinetic energy associated with a particular degree of confinement. A light particle resists being squeezed into a small region through vigorous quantum motion. A heavier particle can be localized with a smaller kinetic energy cost. Imagine trying to keep two objects near the bottom of a gently curved bowl. A pair of light table tennis balls may bounce around easily, while heavier balls move more slowly and remain closer to the low point. Quarks are not classical balls, but the comparison offers a reason heavy components can encourage binding. The attraction does not have to fight quite as much restless motion. Two heavy quarks can therefore form a relatively compact core. Lighter antiquarks may move around this core and provide the colour needed to make the full tetraquark neutral. In some models, the heavy diquark acts almost like the central component of a heavy baryon, except that its colour relationship is balanced by two antiquarks, rather than by a third quark. This does not mean that every combination containing heavy quarks must bind. The attractions still compete with the energies of alternative meson pairs. The same heavy quarks may each join a light antiquark, forming two separate heavy mesons. The tetraquark will be stable only if the four-body arrangement is energetically more favourable than this division, or if quantum rules make the division unusually difficult. Mass differences among quark flavours can shift this balance. Replacing charm quarks with heavier bottom quarks may strengthen the chance of deep binding in certain predicted tetraquarks. The heavier quarks contribute less disruptive motion, while their attractive colour interaction remains. For this reason, some of the most promising theoretically stable tetraquarks involve two bottom quarks and two light antiquarks. These predicted particles may lie below all available strong decay thresholds. If so, they could not immediately split into ordinary mesons through the strong interaction. They would have to decay through the weak interaction, giving them lifetimes much longer than those of typical hadronic resonances. Longer is a relative word here. No one would have time to name one individually or offer it a biscuit, but detectors might receive a much clearer record of its journey. Charm quarks provide a less deeply bound situation. A doubly charmed tetraquark may lie extremely close to the threshold of two charm mesons. Such a state can be very narrow because there is little energy available for its decay. The decay products emerge slowly relative to one another, and only a small region of possible motion is open to them. This shortage of available motion is called limited phase space. The phrase sounds as though particles have failed to book a large enough venue, but it describes the number of ways energy and momentum can be distributed among the products. A decay with plenty of excess energy has many possible arrangements. A decay occurring barely above threshold has very few. Fewer available outcomes can reduce the decay rate and make the parent state narrower. Not every tetraquark needs a compact diquark structure. Four constituents can hold together because they are already organized into two color neutral mesons. The attraction between these mesons is weaker than the force acting directly among colored quarks, but it may still be sufficient when the mesons are close to threshold. This residual strong force is related to the force binding protons and neutrons inside nuclei. A proton is color neutral. A neutron is color neutral, yet they attract, because the fields inside them extend beyond the simplest picture of sealed neutral objects. At suitable distances, exchanges involving light mesons can carry an effective force between the hadrons. Two heavy mesons may interact in a similar way. One or more light particles can be exchanged between them, producing attraction in certain combinations of spin and flavour. If the attraction is just strong enough, the mesons can form a shallow bound state. The result is a hadronic molecule. A shallow state sits only slightly below the threshold of its separate components. its binding energy is small, and its average size may be larger than that of a compact hadron. The mesons retain much of their separate identity. They are connected, but not merged into one tightly packed cluster. The deuteron provides a useful comparison. It is the nucleus of heavy hydrogen and contains one proton and one neutron. The proton and neutron are each complete hadrons, yet the residual strong interaction binds them into one nucleus. The deuteron is weakly bound compared with the internal binding of quarks inside either nucleon. A hadronic molecule would be similar in spirit, though it would often be far less stable and would involve mesons rather than a proton and neutron. Light-meson exchange is not the only contribution to molecular attraction. Shorter range effects, exchanges of heavier particles, and direct rearrangements of the underlying quarks may all matter. At very small separations, the idea of two untouched mesons becomes less reliable because their internal fields overlap. The quarks can change partners, and colour arrangements that were hidden inside the individual hadrons can become important. Suppose the tetraquark begins in a meson-like arrangement. One quark is paired mainly with one antiquark, while the remaining pair forms the second meson. Gluon exchange can recouple the colours, so that the original pairs are no longer neutral separately. The complete system remains neutral, but the internal colour is now distributed across all four constituents. These configurations are sometimes called hidden colour arrangements. They cannot be separated directly into two observable colour-neutral hadrons without another rearrangement. Hidden colour does not mean that colour charges become invisible through secrecy or excellent camouflage. All colour charge is hidden from direct observation by confinement. The term indicates an internal coupling that is neutral only when all four constituents are considered together. A compact tetraquark may contain a substantial hidden colour component. A loose molecule is expected to be dominated by two colour-neutral hadrons at large separation. As the components move closer, however, even a molecular state can develop compact and hidden colour contributions. The categories begin to overlap. This leads to one of the deepest reasons four quarks can remain together. They are not locked into a single pattern. The quantum state can move among several configurations, and the mixing itself can lower the energy. In quantum mechanics, two possible arrangements with the same overall properties can interact. Instead of remaining as separate states, they combine into new mixtures. One mixture may move upward in energy while the other moves downward. The lower mixture can become more strongly bound than either simple arrangement would have been alone. This effect is common throughout physics. Atomic orbitals combine to form molecular orbitals. Different particle states mix when their quantum numbers permit it. Even ordinary mesons can contain mixtures of quark flavours. A tetraquark may similarly gain stability because compact, molecular, diquark and meson pair configurations are not isolated possibilities. They contribute together to the real state. The result can be a particle that looks molecular in its mass but compact in its production. A state extremely close to a meson threshold may have a large loose component, yet it may also contain a smaller compact core. The large component determines much of its spatial structure, while the compact component allows it to form efficiently in a high-energy collision. This helps explain why arguments based on one measurement can be misleading. A small binding energy may strongly suggest a molecule. A high production rate may suggest a compact object. Both clues can be correct if the particle is mixed. Asking which description is true may be less useful than asking how much each configuration contributes. Spin provides another source of attraction and selection. Quark spins can align or oppose one another, changing the energy of the state. The strong interaction includes spin-dependent effects, and some combinations are energetically preferred. A tetraquark with one total spin may bind, while a similar arrangement with a different spin does not. Parity and other quantum properties also determine which decay channels are available. A tetraquark may possess enough mass to produce two mesons, yet the decay can be suppressed if the final particles cannot easily reproduce the parent state's angular momentum and parity. They may need to emerge with additional orbital motion, which reduces the decay probability near threshold. This can create a narrow resonance above the energy of its possible decay products. The state is not protected by insufficient energy, but the quantum route out is awkward. It is like standing beside an unlocked door that can be reached only by performing a very precise turn while carrying several suitcases. Escape is possible, though not especially efficient. Flavor can create similar obstacles. A state containing heavy quarks may need to rearrange them into particular mesons. Some decays require the creation of a new quark and antiquark pair. Others require a heavy quark and antiquark to annihilate, which may be less likely if they spend little time close together. The internal structure therefore influences which exit routes the particle can find. A molecular state made from two mesons can decay through the decay of one of its components. If one meson is unstable, the molecule may inherit that instability. Its lifetime can resemble that of the constituent, modified by the small binding energy and the surrounding partner. A compact tetraquark may decay through a more extensive rearrangement. Its quarks and antiquarks must reorganize into color-neutral final hadrons. If that rearrangement is easy and releases substantial energy, the state will be broad. If it requires an unfavorable color, spin, or spatial change, the state may be narrower than its mass alone would suggest. The spatial overlap of the wave patterns matters. A decay occurs more readily when the internal arrangement of the parent resembles the arrangements of the products. If a tightly bound tetraquark must transform into two large mesons with very different internal motion, the overlap may be small. If it already resembles those two mesons, falling apart can be easy unless its energy lies below their threshold. This creates an interesting reversal. A molecule may be held only weakly, but if it lies below threshold, it can be narrow. A compact state may be bound strongly inside, yet decay rapidly because its mass lies above several accessible channels. Tight internal attraction does not automatically produce a long lifetime. The surrounding quantum vacuum also participates. A tetraquark is not isolated from every possible particle state. It can fluctuate into virtual meson pairs and back again. These couplings can shift its measured mass. A conventional meson close to a threshold may acquire a large molecular component, while a molecular state may borrow properties from a nearby compact configuration. For this reason, the mass observed in an experiment is not always the mass predicted by a simple model, containing only 4 fixed constituents. Interactions with nearby channels can pull the energy upward or downward. They can change the width and reshape the resonance. A particle near threshold may not even follow the simple symmetric peak expected for an isolated resonance. Physicists use several theoretical methods to study these effects. Models based on constituent quarks estimate the attractions among different color and spin arrangements. Effective field theories focus on the low-energy interactions of hadrons near thresholds. Quantum chromodynamics can be simulated numerically on a lattice representing points in space and time, allowing researchers to study how the underlying quark and gluon fields produce bound states and scattering behavior. Each method sees the problem from a different distance. A quark model looks inward at possible compact arrangements. A molecular theory begins with hadrons as the useful components. A lattice calculation attempts to connect more directly with the fundamental theory, though practical limitations remain. Agreement among these approaches can strengthen a conclusion, while disagreement often reveals which physical ingredients have been neglected. There is no single force named the Tetraquark force. 4 quarks hold together through the same strong interaction that builds ordinary mesons and baryons. What changes is the balance among color attraction, quantum motion, quark masses, spin relationships, threshold positions, and the availability of decay channels. Some combinations never produce a distinct state. Their constituents simply reorganize into conventional hadrons. Others create broad resonances that are difficult to separate from the background. A few occupy fortunate positions where attraction is strong, kinetic energy is manageable, and easy decay routes are closed or restricted. Those states can appear as narrow, convincing particles. The existence of a tetraquark therefore depends as much on what it cannot become as on the forces holding it together. A state below its easier strong decay threshold remains trapped. A state with inconvenient quantum numbers escapes slowly. A state containing heavy quarks may gain stability because their motion is subdued. A state near a meson threshold may bind through a delicate residual attraction. There is something rather elegant about this. Four quarks do not remain together because nature introduces a new rule for them. They remain together because the old rules have more consequences than the early hadron classification revealed. Color charge permits several neutral arrangements. Gluon exchange connects those arrangements. Heavy masses reduce some of the restless motion. Quantum mixing lowers certain energies. Conservation laws close some exits while leaving others only partly open. The Tetraquark is therefore not a violation of the old physics. It is a less obvious performance of the same physics. The strong interaction was always capable of richer structures, but most of those structures are difficult to form and even harder to preserve. Ordinary mesons and baryons dominate because they are often the simplest destinations for confined quarks. Tetraquarks occupy the rarer places where four constituents find a collective arrangement that lasts long enough to leave a recognizable trace. No detector watches this binding happen directly. The color exchanges occur at distances far too small and over times far too short. Scientists see only the particles entering a collision, the decay products leaving it, and the statistical patterns repeated across enormous collections of events. From those patterns they infer whether the four constituents briefly formed one state, how tightly that state was bound, and which internal picture best explains its behavior. The mechanisms give physicists a set of expectations. A loosely bound molecule should appear near the threshold of its component mesons, and may have characteristic decays. A compact diquark and anti-diquark state may belong to a wider family of related particles. A deeply bound system containing heavy quarks may be unable to decay strongly. A mixed state may reveal one personality in its mass and another in the way it is produced. Those expectations can now be compared with real events. Particle accelerators have supplied the collisions. Detectors have recorded the tracks. Independent experiments have watched unusual signals return with increasing clarity. The next step is to follow how several of those signals moved from uncertain bumps in data to recognized members of a new and expanding family of matter. Knowing how four quarks might hold together is one thing. Finding evidence that they have actually done so is another. The strong interaction operates at scales far smaller than anything a microscope can reach, and most tetraquarks survive for less time than light needs to cross an atomic nucleus. No detector has ever displayed a tidy image of four quarks sitting together. There is no photograph showing two quarks on the left, two antiquarks on the right, and a small sign in the middle confirming that everyone belongs to the same particle. Instead, tetraquarks reveal themselves by falling apart. This may sound like an inconvenient way to discover something, but particle physics has become extremely good at learning from debris. High-energy collisions create unstable particles. Those particles decay into lighter particles, which may decay again before finally reaching the detector. Researchers record the paths, charges, energies and directions of the surviving products. They then work backwards, reconstructing the short-lived parents that must have existed earlier in the event. It is a little like entering a kitchen after a particularly ambitious cake has collapsed. Flour covers the counter, a bowl is rolling beneath the table, and someone has placed a whisk in the sink with an expression of complete innocence. You did not witness the exact sequence, but the evidence allows you to reconstruct a fairly convincing history. A modern particle detector is built from several layers, each designed to measure a different part of that history. Tracking systems follow the paths of electrically charged particles through magnetic fields. Because positive and negative charges curve in opposite directions, the bending reveals the sign of the charge. The amount of curvature helps determine the momentum. Other detector layers measure energy. Dedicated systems help distinguish electrons, muons, pions, kaons, protons, and other particles that might otherwise leave similar tracks. Computers combine all this information and search for groups of decay products that appear to have come from the same point. When the measured energies and momenta are considered together, researchers can estimate the mass of the particle that produced them. If the same reconstructed mass appears repeatedly, more often than known background processes can explain, a peak begins to rise in the data. This peak is sometimes called a bump. The word sounds almost disappointingly gentle. Years of accelerator operation, thousands of scientists, enormous detectors, and vast computing systems may all lead to a small bump on a graph. Yet that bump can represent an entirely new form of matter. The first major signal in the modern Tetraquark story appeared in 2003 at the Bell experiment in Japan. Bell was installed at the KEKB electron and positron collider. Electrons and their antimatter partners were accelerated in opposite directions and collided, producing large numbers of particles containing bottom quarks. These particles, known as B mesons, offered a rich source of unusual decays. A bottom quark decays through the weak interaction, often producing charm quarks among its descendants. Because the decay occurs through several steps, a B meson can create combinations that are difficult to produce in simpler collisions. Bell researchers examine millions of these events, searching for recognizable particles hidden within the final tracks. In one group of decays, they reconstructed a JPSI particle accompanied by two pions. The JPSI was already known as a conventional charmonium state containing a charm quark and a charm antiquark. When Bell combined the JPSI with the two pions, an unexpected narrow peak appeared at a mass near 3,872 million electron volts. The new state became known as X3872. The letter X expressed uncertainty because the particle did not have an obvious place in the existing charmonium family. It looked related to charmonium because it decayed into a JPSI, but its mass and narrow width did not agree comfortably with the conventional levels expected in that region. Its mass was especially interesting because it sat almost exactly beside the threshold for a neutral D meson and a neutral D star meson. A D meson contains a charm quark paired with a light antiquark. A D star is a related excited meson. The closeness suggested that X3872 might be a molecule formed from those two mesons. It might instead contain four quarks in a more compact arrangement, or it might mix a molecular component with ordinary charmonium and compact tetraquark components. The discovery did not answer that question. What it did was establish a particle that the old rulebook could not explain easily. Other experiments soon confirmed the state. Babar in the United States, CDF at the Tevatron, and later LHCb and other detectors observed it through different production processes. This independent confirmation mattered. A signal seen by only one detector might arise from an unnoticed problem, an inaccurate background model, or statistical chance. A state that appears in several machines, using different collision types and analysis methods, becomes much harder to dismiss. X3872 did not provide a simple declaration that tetraquarks had arrived. Its electric charge was neutral, so it could in principle contain only a charm quark and charm antiquark. Its unusual behaviour made it an exotic candidate, but its quantum properties did not force a four-constituent interpretation. A more direct clue arrived in 2007, again from Bell. Researchers were examining B meson decays that produced a kaon, a pion, and an excited charmonium particle called psi prime. When they combined the psi prime with the charged pion, they found evidence of another structure. It became known as Z4430. The letter Z was used for a charged charmonium-like state. That charge changed the nature of the argument. The psi prime already contained a charm quark and charm antiquark. Together, those two constituents had no net electric charge. The parent Z particle was charged, so it needed additional quark content. At least one light quark and one light antiquark had to be involved. This meant that Z4430 could not be an ordinary charmonium meson. Its minimum content required 4-quark constituents. On paper, it looked like exactly the sort of manifestly exotic state physicists had been seeking. The data, however, came from a complicated decay. The kaon and pion could combine into several known resonances. Those resonances created patterns that might imitate a peak in the cis prime and pion combination. Bell concluded that the new charge structure was needed, but the Babar experiment later studied a related sample and did not find significant evidence for it. For a while, Z4430 sat in an uncomfortable position. It was too interesting to ignore and too disputed to accept without reservation. More data and a more powerful analysis were required. That analysis came from the LHCb experiment at the Large Hadron Collider. LHCb was designed to study particles containing bottom and charm quarks. Unlike the large general-purpose detectors surrounding nearly the entire collision point, LHCb extends mainly in one direction. This shape is suited to the way heavy hadrons are produced in proton collisions, often travelling forward near the path of the original beams. The Large Hadron Collider produces an immense number of bottom-containing particles. LHCb can identify their decay points with exceptional precision. Bottom hadrons travel a measurable distance before decaying, leaving a secondary point separated from the original proton collision. This tiny displacement helps researchers isolate them from the much larger number of ordinary particles created in the same event. In 2014, LHCb examined a large collection of the decays associated with Z4430. The researchers did more than search for a peak. They constructed a detailed model of the complete decay, including the known resonances formed by the kaon and pion. They studied the masses and angular relationships of the final particles together. The known kaon resonances could not explain the data. A charged component decaying into the psi prime and pion was required with very high statistical confidence. LHCb also observed something more decisive. A genuine resonance does not simply cause more events to appear near one mass. Its quantum amplitude changes in a characteristic way as the reconstructed mass passes through the resonance. The strength changes, but so does a property called phase. Phase is difficult to picture because it belongs to the wave-like description of quantum events. A useful comparison is a driven swing. If someone pushes a swing slowly, its motion follows the pushing in one way. Near the natural rhythm of the swing, the response grows and its timing shifts. Above that rhythm, the timing changes again. A resonance carries a related pattern in the relationship between the driving process and the response. LHCb measured this phase movement for Z4430. The result traced the looping behaviour expected from a genuine resonant particle. The bump was not merely a reflection cast by another part of the decay, the state had its own dynamic identity. This was a major turning point. Here was a charged particle containing hidden charm, confirmed through a detailed amplitude analysis and shown to behave like a true resonance. Whatever its precise internal architecture, an ordinary quark and antiquark meson could not explain its constituent requirements. Around the same period, another charged state strengthened the case. In 2013, the BES-3 experiment in China studied electron and positron collisions at an energy where the unusual Y4260 state was produced. Among its decay products, BES-3 observed a charged structure combining a JPSI with a pion. The particle was called ZC3900. Bell independently reported a compatible signal using a different method. A later analysis by the CLEO experiment also found evidence consistent with the same state. The near-simultaneous observations were important because they reduced the chance that the signal came from a detector-specific effect. Like Z4430, ZC3900 carried electric charge while decaying into charmonium. It therefore required additional light quarks beyond the charm and anti-charm pair. Its mass was close to the threshold for two open charm mesons, encouraging interpretations involving a hadronic molecule or a threshold resonance. Compact tetraquark models were proposed as well. BES-3 continued studying the region and found additional charged structures, including ZC4020. Bell had already observed bottom-related partners called ZB states, which contained a bottom quark and bottom antiquark along with light constituents. What had initially seemed like one or two unusual particles was beginning to look like a pattern, extending across different heavy quark flavors. The experiments were not merely collecting more names, they were revealing repeated behavior. Charged states appeared beside charmonium or bottomonium. Many sat near thresholds where pairs of ordinary mesons could form. Some decayed into both hidden heavy flavor channels and open heavy flavor channels. The growing family suggested that the strong interaction had several ways of organizing four constituent systems. The Large Hadron Collider then opened access to even more unusual combinations. Proton collisions contain enough energy to produce many heavy quark pairs in the same event. LHCb used these collisions not only to study particles containing one charm quark and one charm antiquark, but also to search for arrangements whose flavor content could not resemble ordinary charmonium at all. In 2020, LHCb examined pairs of JPSI particles. Each JPSI contains a charm quark and charm antiquark. Producing two of them in the same final state therefore provides a natural place to search for a particle involving two charm quarks and two charm antiquarks. When researchers plotted the reconstructed mass of the JPSI pairs, they observed a broad structure near the lowest accessible region and a narrower peak around 6,900 million electron volts. The narrower structure became known as X6900. A particle decaying into two JPSI mesons could have the minimal content of two charm quarks and two charm antiquarks. Such an object is called fully charmed because all four valence constituents belong to the charm flavor. No light up, down, or strange quarks are needed in the minimum description. Fully charmed states are valuable because they offer a cleaner laboratory for studying the strong interaction. The constituents all have substantial mass, and interpretations involving the exchange of very light mesons are less central than in many molecular candidates. Yet X6900 still did not arrive with a final internal diagram. It could be a compact, fully charmed tetraquark, a resonance related to pairs of charmonium states, or a mixture influenced by nearby thresholds. The signal was important enough that other Large Hadron Collider experiments investigated it. CMS and Atlas found structures in the same general JPSI pair spectrum, including evidence compatible with X6900 and additional possible all-charm states. By 2025, Atlas reported a strong independent confirmation of the X6900 candidate using several channels containing pairs of charmonium particles. The fully charmed region was no longer a curiosity belonging to one experiment. Multiple detectors had begun mapping what appeared to be a family. Differences among the measured shapes and additional peaks remained under study, but the repeated appearance of structure showed that four heavy quark systems were a real part of hadron spectroscopy. Another breakthrough came in 2021, when LHCb reported a particle with two charm quarks and two light antiquarks. It became known as the TCC+ state, with the repeated C indicating its two charm constituents. This combination was remarkable because it contained two charm quarks, rather than a charm quark paired with a charm antiquark. Ordinary charmonium could not imitate it. An ordinary meson could contain only one quark and one antiquark. A conventional baryon could contain two charm quarks, but it would need a third quark rather than two antiquarks. The observed state therefore introduced a genuinely new flavor arrangement. LHCb found it in a spectrum, containing two neutral d mesons and a charged pion. The signal appeared extremely close to the threshold of a neutral d meson and a charged D-star meson. It was extraordinarily narrow, narrower than the previously known Tetraquark candidates. The position of the peak suggested that the state was bound by only a very small amount. It may behave mainly like a molecule formed from two charm mesons. The two charm quarks are separated into different mesons in that picture, while the light antiquarks complete the pair. A compact component may also contribute, but the closeness to threshold provides strong evidence for an extended molecular structure. This discovery was especially satisfying because theorists had long predicted that tetraquarks with two heavy quarks might be more stable than many hidden charm states. The heavy quarks could help reduce the kinetic energy and create favourable binding. LHCb had found the first observed example containing two charm quarks with no matching charm antiquarks. The narrowness of the TCC plus state allowed physicists to study its threshold behaviour with unusual precision. Instead of seeing only a broad hill in the data, they could examine the line shape and decay channels in detail. This supplied information about the attraction between charm mesons and the internal scale of the state. In 2022, LHCb added another striking pair. Researchers observed a doubly charged tetraquark candidate and a neutral partner. These states contained a charm quark, a strange antiquark, and two light constituents arranged so that one member carried 2 units of positive electric charge. A doubly charged meson-like object is difficult to hide inside the ordinary rulebook. The electric charge and flavour combination require 4 constituents. The discovery of a neutral partner with a related mass strengthened the interpretation that the two belong to the same isospin family. The relationship between these two states was as important as either peak alone. Particle families often reveal underlying quark structure more clearly than isolated particles do. If a model explains one member, it should predict partners with related charges, masses, and decay patterns. Finding those partners tests whether the proposed arrangement is genuinely part of the strong interaction, or merely a convenient story attached to one signal. Across these experiments, no single detector performed the entire discovery. Bell supplied the first narrow charmonium-like mystery, and the first evidence for important charged candidates. Babar challenged some early claims and confirmed others. BES3 revealed charged states through precision electron and positron collisions. LHCb used enormous samples of heavy hadrons to establish resonant behaviour and discover new flavour combinations. CMS and Atlas extended the fully heavy searches and tested whether LHCb signals appeared independently. This cooperation and disagreement are both essential. A new particle becomes trustworthy not because one group is enthusiastic, but because different groups can attack the result from different directions. They use different detectors, backgrounds, collision environments, and analysis choices. When the same structure survives all of them, confidence grows. There is also a hierarchy in what the experiments reveal. A peak suggests that something unusual may be present. Independent confirmation shows that the feature is reproducible. An amplitude analysis can establish resonant behaviour. Measurements of charge and flavour determine whether an ordinary meson is possible. Spin and parity restrict the internal models. Decay rates and threshold positions provide clues about whether the structure is compact, molecular, or mixed. Each stage requires more data. It also requires patience, because the most interesting interpretation is not always the correct one. Several claimed exotic states have weakened or disappeared under later investigation. Their absence from the final catalogue is not wasted effort. They teach researchers which backgrounds are deceptive and which analysis methods need improvement. The tetraquarks that remain have passed increasingly demanding tests. They do not all look alike. Some are broad and sit above several decay thresholds. Others are so close to a threshold that they appear barely bound. Some contain a heavy quark and its antiquark. Others contain 2 heavy quarks of the same flavour. Some carry ordinary electric charge, while one observed family includes a doubly charged member. The fully charmed candidates contain no light valence constituents at all. The experiments have therefore revealed more than the existence of one four-quark particle. They have uncovered a varied landscape of exotic hadrons. The strong interaction can produce compact resonances, molecule-like states, and perhaps mixtures whose character changes depending on how they are observed. That variety leaves one major problem unresolved. Detecting a tetraquark does not automatically tell us how its four constituents are arranged. A peak may be clear, its charge may demand four quarks, and its resonant nature may be secure, while its interior remains disputed. The next task is to decide whether these particles are small and tightly connected, large and molecular, or suspended somewhere between those two pictures. The experiments had established that four quark states were real, but they had not settled what those states looked like inside. A detector could reveal a particle's mass, electric charge, lifetime, spin and decay products. It could show that a conventional quark and antiquark meson was not enough to explain the result. What it could not do was open the particle and display its internal arrangement. The same four constituents might form one tightly connected object, two ordinary hadrons held together at a greater distance, or a quantum mixture that contains features of both. This is the central difficulty in understanding tetraquarks. Discovering that a state exists is not the same as determining how it is built. The two most familiar possibilities are usually described as the compact tetraquark and the hadronic molecule. The names suggest a clear choice. One sounds small and tightly packed. The other sounds large and loosely connected. In simple diagrams, the difference appears obvious. A compact tetraquark is drawn as four quarks joined within one boundary, while a molecule is drawn as two mesons resting beside one another. The real distinction is less tidy. Quarks are not fixed beads, hadrons do not have perfectly sharp edges, and a quantum state can contain several configurations at once. The drawings are useful starting points, but they should not be mistaken for photographs. In a compact tetraquark, the four valence constituents participate strongly in one integrated colour structure. The two quarks might form a correlated d-quark, while the two antiquarks form an anti-d-quark. These clusters carry colour charge and therefore cannot exist separately, but their colours can combine so that the complete object is neutral. Another compact arrangement may involve colour connections distributed among all four constituents without two clear clusters. Gluons move between the quarks, changing the internal colour relationships. At one moment, a particular pairing may provide a useful description. At another, a different pairing may become more important. The defining feature is that the state cannot be understood mainly as two complete colour-neutral mesons sitting far apart. A compact tetraquark would normally be expected to occupy a region similar in size to that of an ordinary hadron. The quarks would interact over short distances, and hidden colour arrangements could play a major role. Hidden colour does not mean that physicists have misplaced the colour charge. It refers to combinations in which neither half of the system is independently neutral. Only the complete four-constituent object has an observable colour, neutral identity. A hadronic molecule begins from a different picture. Each quark is already paired with an antiquark to form an ordinary meson. The two mesons are individually colour neutral, but they can still attract through residual effects of the strong interaction. If that attraction is sufficient, they may form a weakly bound state. This is similar in broad principle to the way a proton and neutron bind to form the deuteron. The proton and neutron are complete hadrons. The quarks inside each one are held by the direct colour interaction, while the force between the two hadrons is a leftover effect. The deuteron is much more loosely bound than the quarks within either of its components. A molecular tetraquark could follow the same hierarchy. The quarks inside each meson would be tightly bound, while the connection between the mesons would be much weaker. The full object could therefore be larger than an ordinary hadron, with the mesons spending much of their time separated by a comparatively wide microscopic distance. Calling such a state a molecule does not mean that it behaves like water, oxygen, or any other chemical substance. Chemical molecules are formed from atoms and held together by electromagnetism. Hadronic molecules are made from hadrons and held through the residual strong interaction. The analogy concerns the organization, not the materials involved. There are no microscopic chemistry sets operating inside the accelerator, which is probably useful because the safety paperwork would become unreasonable. The position of a tetraquark's mass often provides the first clue about which picture is more appropriate. If a state appears extremely close to the threshold for two ordinary mesons, a molecular interpretation becomes attractive. The threshold is the minimum energy needed to produce those mesons separately. A state lying just below it can be understood as a weakly bound pair. Only a small amount of energy would be required to separate the components. The particle known as X3872 is the best known example of this problem. Its mass lies extraordinarily close to the combined mass of a neutral d meson and a neutral d star meson. This is unlikely to be an irrelevant coincidence. It strongly suggests that these mesons contribute substantially to the particle's structure. If X3872 lies just below the threshold, its binding energy is extremely small by the standards of the strong interaction. A shallow binding energy usually corresponds to a large average separation between the components. This would make the state resemble a loose molecule more than a tightly packed tetraquark. Some of its decay behavior supports that view. The neutral meson combination is especially important, while the small mass difference between neutral and charged charm. Meson thresholds can help explain the unusually large breaking of isospin symmetry observed in its decays. A molecular state located directly beside the neutral threshold would naturally be sensitive to those small mass differences. Yet X3872 does not behave like a completely simple molecule in every measurement. It is produced promptly in high-energy proton collisions, sometimes with substantial momentum. A very large and extremely fragile object might be expected to form with difficulty in such a violent environment. Its production rate has therefore been used to argue that a smaller, more compact component may also be present. This argument is not decisive on its own. Particle production in high-energy collisions is complicated, and a molecular state can form through several routes. The mesons may be produced near one another and bind afterward. A small compact component may assist production even if the particle is mostly molecular at long distances. The final yield depends on the collision environment, the available quarks, and the interactions occurring as the event cools. Radiative decays provide another clue. X3872 can decay by emitting a photon and producing different charmonium states. The relative rates of these decays can depend on whether the particle contains a compact charm and anti-charm core. Some measurements and theoretical studies suggest that a purely extended molecule may not explain every radiative transition easily. Once again, this does not force the particle into the compact category. It may mean that its internal state contains both a large meson molecule component and a smaller conventional charmonium or compact tetraquark component. The molecule could dominate the outer structure, while the compact part influences processes occurring at short distances. This combination is not an improvised compromise designed to keep everyone happy. Mixing is a standard feature of quantum mechanics. Whenever two configurations have the same overall quantum properties and can interact, the physical states can contain both. Atomic states mix, mesons mix, neutrino flavors mix. There is no reason a tetraquark must be exempt simply because a diagram would be easier to label if it chose one arrangement. Imagine two musical notes produced by separate strings with nearly matching frequencies. If the strings are coupled, their motions no longer remain independent. The actual vibrations become combinations of both strings. One mode may involve them moving together, while another involves them moving against each other. Asking which string owns the sound misses the way the complete system behaves. A tetraquark near a meson threshold can work in a related way. A compact quark configuration may exist near the energy of two interacting mesons. The two possibilities couple. The measured particle becomes a mixture, and the mixing can shift its mass toward the threshold. The state may then appear molecular in some measurements and compact in others, because both features are genuine. The amount of each component can depend on distance. At large separations, the state may look like two mesons. At short distances, where the mesons overlap, quark exchange and hidden color configurations become important. A single percentage may therefore fail to capture the full physical picture. The useful description changes with the question being asked. If physicists study the binding energy and long-distance scattering behavior, the molecular component may dominate. If they examine a decay requiring the charm quark and antiquark to approach closely, the compact component may matter more. The state does not switch identity between experiments. Different experiments probe different parts of the same quantum structure. The doubly charmed state, called TCC+, provides another powerful example. It contains two charm quarks and two light antiquarks. Its signal was observed extremely close to the threshold of a neutral D meson and a charged D star meson. The state is remarkably narrow, and detailed analyses generally support a large molecular component. This makes physical sense. The TCC+ state appears to be only weakly bound. Its two charm mesons can remain recognizable within the combined object, rather like two people sharing a very large sofa, while making only a limited commitment to conversation. Their attraction is enough to keep them together, but not enough to erase their individual identities completely. The TCC+ state may still contain compact configurations at shorter distances. The charm quarks can correlate with each other, and the light antiquarks can rearrange the color structure. The observed state is not required to be a perfect pair of mesons at every instant. Describing it as mostly molecular means that the two meson configuration contributes strongly to its overall behavior. Other Tetraquark candidates look less molecular. Some lie well above the nearest two meson thresholds. They have broader widths and decay through several channels. A loosely bound molecular picture may be less natural for these states because their components would not be trapped near a single threshold. Charged Z states, for example, may contain stronger compact contributions. Their masses, production behavior, and patterns of related states have encouraged dequark and anti-dequark models. In those models, a heavy quark joins a light quark to form a dequark, while the heavy antiquark joins a light antiquark to form an anti-dequark. The two coloured clusters then bind together. A compact model often predicts families of particles. Changing the spin alignment, replacing one light quark flavour with another, or moving the internal motion to a higher state can produce partners with related masses. Discovering those partners would support the idea that Tetraquarks have an organised compact spectrum, just as ordinary mesons and baryons do. Molecular models also predict partners, but their pattern is tied more closely to available hadron thresholds. If two mesons attract in one combination of spin and flavour, related meson pairs may produce additional states. Their masses should appear near the corresponding thresholds, rather than following only the internal excitation pattern of a compact four-quark object. This gives experiments a useful strategy. Instead of examining one particle in isolation, researchers can search for the wider family expected by each model. A proposed compact tetraquark should not be permitted to live alone without explaining where its relatives have gone. A molecular interpretation should identify the mesons involved and predict which similar pairs might also bind. The fully charmed candidates provide another test. These states contain two charm quarks and two charm antiquarks, and can decay into pairs of charmonium particles. Because all four constituents are heavy, some of the light meson exchange mechanisms commonly used for hadronic molecules are less straightforward. Compact arrangements may therefore become more important. Even here the choice is not automatic. Two charmonium particles can interact, and threshold effects can create structure in their combined mass distribution. A peak near a pair threshold might be molecular or generated by coupled channel dynamics. A peak farther from obvious thresholds may provide a stronger compact candidate, but its full resonance behavior still has to be established. The word threshold appears repeatedly because it is one of the most important clues and one of the most dangerous sources of confusion. A genuine bound state can appear near a threshold, so can a resonance. But the opening of a new decay channel can also create a cusp, a sudden change in the shape of the data without a separate particle existing. Imagine traffic moving along a road when a new lane suddenly opens. The flow pattern changes at the opening point, even though no new vehicle has appeared. In particle scattering, a new channel becoming available can similarly change the amplitude and produce an enhancement. A bump close to threshold is therefore not automatically a molecule or even a new resonance. Researchers must study the phase behavior, line shape, and reactions in which the feature appears. A resonance usually corresponds to a pole in the scattering amplitude, a mathematical feature representing a distinct state. The location of that pole and its relationship to the threshold help distinguish a bound state, a virtual state, and a short-lived resonance. A virtual state is especially difficult to picture. It is not a stable particle sitting below threshold in the ordinary bound sense, but it still affects the scattering strongly. Two particles may behave as though they almost form a bound object without quite doing so. Nature occasionally approaches the edge of creating a particle, and then leaves physicists to debate the paperwork. The observed line shape can help separate these cases, but detector resolution and limited data complicate the task. A narrow state may appear broader because the instrument cannot measure the mass perfectly. A threshold can distort a resonance until it no longer looks like the simple peak shown in introductory diagrams. Several nearby channels may overlap and pull the shape in different directions. Decay patterns offer additional information. A molecule should decay readily into channels related to its component mesons. If one component can decay while the other remains largely unaffected, the complete state may inherit that decay. A compact tetraquark may favour rearrangement into several different meson pairs, depending on the overlap between its internal wave pattern and those of the final particles. The relative strengths of these decays can expose the internal structure. A state that overwhelmingly returns to the mesons associated with its threshold supports a molecular interpretation. A state that decays strongly into several channels, not obviously related to one molecular pair, may require a more compact component. Production provides another set of tests. A compact tetraquark could form early in a collision when quarks are close together. A hadronic molecule might form later, after ordinary mesons have emerged and move with similar velocities. These mechanisms can produce different patterns in proton collisions, heavy ion collisions, and decays of heavier particles. Heavy ion collisions are particularly interesting because they create a hot, expanding medium containing many quarks and hadrons. A large molecule may form through the later coalescence of mesons, while a compact tetraquark may emerge earlier from nearby quarks. Their yields and momentum distributions could therefore differ. The medium can also destroy fragile states. A loosely bound molecule moving through a dense environment may be broken apart by collisions. A compact tetraquark might survive more easily, though it can still interact with the surrounding matter. Measuring how exotic states are produced and suppressed in different collision systems may eventually reveal their sizes and formation times. Lattice quantum chromodynamics offers another route. In lattice calculations, space and time are represented by a finite grid, and powerful computers simulate the behavior of quark and gluon fields. Researchers create mathematical operators designed to resemble compact tetraquarks, meson molecules, and conventional quarkonium states. They then study how strongly the calculated energy levels respond to each operator. This method can reveal whether a state appears in the fundamental theory without relying entirely on a simplified model. It can also provide information about meson scattering and whether an interaction produces a bound state or resonance. The calculations remain demanding, especially when several decay channels and light quarks are involved, but they are becoming increasingly important. Even lattice results must be interpreted carefully. An operator that looks molecular can overlap with a compact state because the underlying quantum fields are connected. A compact operator can create a state with strong meson components. The labels describe how researchers ask the question, not necessarily how nature divides the answer. This brings us back to the possibility of something in between. That phrase may sound vague, but it can be the most accurate description. A tetraquark can be dominated by a molecule at long distance while containing a compact core. It can begin as a conventional quarkonium state whose mass is shifted and reshaped by coupling to nearby mesons. It can be a compact state that spends much of its lifetime fluctuating into two hadrons. These possibilities form a continuum rather than three isolated boxes. At one end is a large, shallow molecule composed mainly of two recognizable mesons. At the other is a compact four-quark object with strong hidden color and diquark correlations. Between them are mixed states with varying amounts of each structure. The balance may differ across the Tetraquark family. X3872 appears to have a major molecular component and possibly a short-range compact core. TCC+ also shows strong molecular characteristics. Some charge Z states may be more compact or may arise from strong interactions directly above threshold. Fully heavy candidates may occupy another region of the spectrum. It would therefore be misleading to demand that all tetraquarks share one architecture. Ordinary matter already shows enormous structural variety. Carbon atoms can form diamond, graphite, graphene, and many molecules. The same particles participate in different organizations because the interactions allow several energy arrangements. Quarks should be granted at least the same freedom as carbon, which has been showing off for quite some time. The important discovery is not that physicists have found one new shape and named it Tetraquark. It is that the strong interaction supports an entire range of four constituent structures. Some resemble molecules, some may be compact. Many combine the two descriptions. Their internal form depends on flavor, spin, color, mass, thresholds, and the decay channels surrounding them. This is why the question remains open even after a particle has been confirmed. Measurements can gradually reveal how large the state is, which components dominate, and how its structure changes across different processes. No single observation is likely to provide the full answer. Mass, width, decays, production, partner states, scattering, and lattice calculations must all be considered together. The uncertainty is not a sign that the tetraquark idea has failed. It is evidence that the discovery has exposed a deeper level of the strong interaction. The old meson and baryon categories were defined mainly by constituent counting. Exotic hadrons require physicists to understand organization as well as ingredients. Once that shift is made, tetraquarks stop looking like awkward exceptions. They become laboratories for learning how quantum chromodynamics turns quarks and gluons into observable matter. Their mixed identities, threshold behavior, and competing internal structures show that a particle is not always a simple container, with one permanent arrangement inside. That change reaches beyond the classification of a few short-lived resonances. It alters what physicists mean when they say that matter is built from quarks. The important question is no longer only which quarks are present. It is how the strong interaction connects them, how several structures can coexist, and why certain arrangements become particles while others remain brief encounters. Following that question leads directly to what tetraquarks changed about the nature of matter itself. For a long time, the basic story of matter seemed to become simpler the deeper physicists looked. Ordinary objects were made from molecules. Molecules were made from atoms. Atoms contained electrons and nuclei. Nuclei contained protons and neutrons. Protons and neutrons contained quarks. Each step removed some of the apparent complexity and replaced it with a smaller set of ingredients. By the time the quark model had organized the hadrons, it appeared that nature had provided a compact rulebook. Quarks could gather in groups of 3 to make baryons, or a quark could pair with an antiquark to make a meson. Nearly every known strongly interacting particle fitted one of those arrangements. Tetraquarks did not show that the ingredients were wrong. They showed that the possible arrangements were much richer than the old picture suggested. That is the most important change they brought to our understanding of matter. The quark model had often been presented like a set of construction instructions. 3 quarks make one type of particle, 1 quark and 1 antiquark make another. Tetraquarks revealed that these were not the only buildings permitted by the materials. They were simply the structures nature produced most commonly and preserved most clearly. 2 quarks and 2 antiquarks can also form an observable state. Sometimes they may gather into a compact object. Sometimes they may remain grouped into 2 mesons that bind together. Sometimes the real state may move between those descriptions. The old categories were not overthrown, but they were placed inside a larger system. This distinction matters because science often advances by discovering that a successful rule was local rather than universal. A map can describe every road in one town perfectly, and still tell us nothing about the roads beyond the town boundary. The meson and baryon model was an excellent map of familiar hadrons. Tetraquarks showed that the strong interaction had been building beyond its marked edge. The discovery also changed the meaning of the phrase elementary building block. Quarks are elementary as far as experiments can currently determine. No smaller components have been found inside them. Yet knowing the elementary ingredients does not automatically tell us every form of matter those ingredients can create. This is already familiar in other parts of science. Knowing that a material is made from carbon atoms does not tell us whether it will become diamond, graphite, soot, or part of a living cell. The same type of atom can participate in very different structures. The organization matters as much as the ingredient list. Quarks follow the same general lesson, though under very different physical rules. A charm quark is still a charm quark whether it appears in an ordinary meson, a baryon, or a tetraquark. What changes is the network of colour interactions around it. The strong force connects the constituents differently, and those connections create particles with different masses, lifetimes, charges, and decay patterns. Matter is therefore not defined only by what is present. It is also defined by how the parts are connected. Tetraquarks made that idea impossible to ignore. In a compact state, 4 constituents may share one colour structure that cannot be divided cleanly into 2 ordinary mesons. In a molecule-like state, the same number of constituents may be organised into 2 colour-neutral hadrons held by a weaker residual force. Both arrangements contain 2 quarks and 2 antiquarks, yet they can differ greatly in size and internal motion. The ingredients alone do not settle the identity. This is a more general lesson about particles. The word particle can make an object sound simple and indivisible. An electron appears to fit that description. It has no known internal structure. A proton does not. It is a composite quantum system full of quarks, antiquarks, gluons, and energy. A tetraquark is even more obviously dependent on organization. It may not possess one permanent internal shape. Several configurations can contribute to the same physical state. A compact 4-quark component can mix with 2 meson components. A conventional quark and antiquark state can be distorted by a nearby molecular channel. The observed particle may contain all of these contributions in different proportions. That makes hadron classification less like sorting stones by shape and more like identifying musical chords. A chord cannot be understood only by listing the notes. Their relationship, spacing, and timing determine what is heard. The same notes can contribute to several musical structures. In a hadron, the quark flavors are important, but so are color, spin, motion, and the available ways the system can rearrange. Tetraquarks also changed how physicists test quantum chromodynamics. Quantum chromodynamics is the theory describing quarks, gluons, and the strong interaction. It had already succeeded in explaining a great deal before tetraquarks were confirmed. It described why quarks become more weakly coupled at very short distances, and why they remain confined inside color, neutral hadrons at ordinary energies. Yet the theory becomes difficult to calculate in the energy range where hadrons form. The fundamental rules are known, but their large-scale consequences are complicated. This is not unusual. The equations describing the atmosphere are known, but predicting every cloud remains difficult. Knowing the rules of chess does not mean knowing the result of every possible game. Ordinary mesons and baryons supplied important tests of the theory, but they represented only the simplest colour-neutral combinations. Tetraquarks provide a more demanding test. 4 constituent systems contain more possible colour arrangements, more ways to distribute spin, and more opportunities for one configuration to mix with another. If physicists can explain why one tetraquark binds while a closely related combination does not, they learn something deeper about the strong interaction. If they can predict a family of partner particles before experiments find them, their model gains credibility. If the predicted partners fail to appear, the model may be incomplete. Each new tetraquark therefore works like a stress test for our understanding of confinement. It asks the theory to explain not merely why quarks cannot escape, but why they choose one colour-neutral arrangement over another. The existence of tetraquarks also blurred the boundary between particle physics and nuclear physics. Ordinary nuclei are made from protons and neutrons. The quarks remain confined inside those hadrons, while residual strong forces bind the hadrons together. A hadronic molecule follows a similar pattern on a smaller and less stable scale. 2 mesons can remain individually colour-neutral, while a leftover strong interaction binds them into one larger state. This means that some tetraquarks may be understood as tiny nuclei made from mesons rather than protons and neutrons. They occupy a region between the usual subjects of particle and nuclear physics. Their components are hadrons, yet the complete object belongs to hadron spectroscopy. The boundary was always partly artificial. The same strong interaction controls quarks inside protons, and the residual forces between protons and neutrons. Tetraquark molecules make the connection visible. They show that nature can build layers of strong interaction structure. Quarks bind into hadrons, and hadrons can sometimes bind into larger hadronic systems. At the other extreme, compact tetraquarks show that the strong interaction can create a single hadron with more valence constituents than the old families contained. These states are not small nuclei. Their quarks may share colour directly across the entire object. Hidden colour configurations can make the whole system neutral, even when no internal pair is independently observable. The tetraquark family may therefore include structures belonging to different levels of organisation. Placing them under one name is useful because they require 4 valence constituents, but their internal physics may not be identical. This changed the way physicists speak about exotic matter. The word exotic once suggested rare, theoretical possibilities resting beyond the established particle spectrum. It sometimes carried the feeling of an optional addition, interesting but perhaps unnecessary. After the discovery of charged harmonium-like states, doubly charmed states, and fully heavy candidates, exotic hadrons became an experimental field rather than a speculative corner. They are still short-lived and uncommon. They do not form the walls of houses or the atoms in our bodies, but they are real consequences of the same force responsible for nearly all the mass of ordinary matter. This point deserves attention. Most of the mass of a proton does not come directly from the small intrinsic masses of its up and down quarks. It comes from the energy of their motion and the strong fields binding the proton together. The mass in everyday objects is therefore already a product of quantum chromodynamics. Tetraquarks reveal additional ways that this mass-generating activity can be organised. A tetraquark mass includes the masses of its quark constituents, but it also contains the energy of gluon fields, quantum motion and binding. The final number depends on the complete structure. Rearranging the same flavours can produce a different mass because the interactions store energy differently. Matter at this level is not a pile of tiny solid pieces. It is a stable or temporary pattern of interacting fields. Tetraquarks made this field-based picture more concrete. A compact tetraquark and a pair of separate mesons may contain the same quark flavours, yet one appears as a distinct resonance while the other behaves as 2 particles. The difference lies in the quantum state of the full system. Even the number of particles can depend on organisation. 4-quark constituents can form one tetraquark or two mesons. The ingredients do not determine whether the result should be counted as one object or two, the interactions do. This may sound unusual, but similar reasoning appears elsewhere in physics. A proton and electron can move separately, or they can form a hydrogen atom. Once bound, the atom behaves as one complete quantum system. It has energy levels and properties that neither separate particle possesses alone. A tetraquark follows the same broad idea, though the strong interaction and confinement make its internal structure far more complicated. One major difference is that most tetraquarks decay almost immediately. They are not permanent pieces of matter, yet unstable particles still belong to the physical world. Stability is not required for existence. A muon decays, a neutron outside nucleus decays. Excited atoms decay to lower energy states. None becomes imaginary simply because it has a limited lifetime. A tetraquark can exist long enough to establish a measurable resonance. It forms with definite quantum properties, influences the motion of other particles, and decays through repeatable pathways. That is sufficient to make it part of nature's particle spectrum. The discovery therefore expanded the meaning of matter beyond the forms that survive around us. Everyday matter is only the portion of the particle spectrum that is stable under current conditions. High-energy collisions briefly reveal other arrangements. They are not foreign to the universe. They are ordinary quantum fields placed in unusual combinations. Early in the universe, temperatures and densities were far greater than anything found naturally on Earth today. Quarks and gluons moved through an extremely hot state before cooling and forming hadrons. Exotic combinations may have appeared during that transition. Most would have decayed rapidly, leaving ordinary protons, neutrons, and other particles behind. Modern accelerators recreate tiny parts of those energetic conditions. When protons or heavy nuclei collide, their energy can produce heavy quarks and complicated hadronic systems. The tetraquarks observed in detectors are therefore glimpses of possibilities that may also have appeared during the universe's earliest moments. They help physicists understand how quarks choose their partners while a high-energy system cools. Do they usually settle into the simplest mesons and baryons? Under what conditions do four constituent states emerge? Does a molecule form later from already completed mesons, or does a compact tetraquark form earlier while the quarks are still close together? These questions connect tetraquark research with the study of the quark and gluon plasma created in heavy ion collisions. A compact tetraquark and a loose molecule may respond differently to that hot medium. One may form early and survive, the other may appear later as the system cools. Measuring their production could eventually reveal the sequence by which hadrons emerge from quarks and gluons. Tetraquarks also changed how researchers search for new particles. Before the exotic hadron era, a new resonance was often compared first with predicted quark and antiquark mesons or three-quark baryons. Now experiments routinely consider multi-quark possibilities, threshold effects, hadronic molecules, and mixed configurations. The analysis itself has become more sophisticated. A simple peak is no longer always enough. Researchers examine the phase movement of the quantum amplitude. They compare several decay channels. They search for charged and neutral partners. They test whether the signal remains when every known background process is included. This caution grew partly from the difficulty of the early discoveries. Some unusual signals disappeared with more data. Others survived but changed interpretation. A feature first called a tetraquark may later be understood as a threshold cusp. A state thought to be compact may turn out to be mostly molecular. The evidence can establish a particle before it establishes the best model of that particle. That separation between observation and interpretation is another lesson tetraquarks reinforced. Science does not require every mystery to be solved at the moment of discovery. Researchers can know that a state exists while openly disagreeing about its interior. This is a strength rather than an embarrassment. The mass, charge, and resonant behavior may be secure facts. The compact, molecular, and mixed pictures are explanations to be tested. Keeping those levels separate prevents confidence in the data from being confused with confidence in one model. The range of observed flavor combinations has also changed theoretical expectations. Hidden charm states contain a charm quark and charm antiquark along with like constituents. Doubly charmed states contain 2 charm quarks and no charm antiquarks. Fully charmed candidates contain 2 charm quarks and 2 charm antiquarks. Strange and bottom-related combinations extend the pattern further. Nature has not produced only one accidental four-quark state. It appears to support a broad landscape. A landscape suggests families, and families suggest rules. Physicists now search for patterns similar to those that once organized the original particle zoo. They ask whether tetraquarks form groups according to flavor and spin. They look for partners predicted by diquark models. They compare states lying near related meson thresholds. The goal is not merely to add more names to a catalogue, it is to find a new order within the exotic spectrum. The particle zoo was simplified once by the quark model. The present collection of exotic hadrons may eventually be organised by a deeper understanding of how colour correlations and hadronic thresholds work together. Fully heavy tetraquarks may become especially useful. A system containing only charm quarks and charm antiquarks removes some of the complications introduced by very light quarks. The constituents remain strongly interacting, but their heavier masses can make certain theoretical approximations more reliable. Bottom quark versions may be even more deeply bound, though producing and detecting them is difficult. Doubly heavy tetraquarks may reveal another important pattern. Theory suggests that some states containing 2 bottom quarks and 2 light antiquarks could lie below every strong decay threshold. Such particles would be unable to split immediately into ordinary mesons. They would decay only through the slower, weak interaction. Finding one would provide an unusually clear example of a stable, strong interaction arrangement beyond ordinary mesons and baryons. It would show that tetraquarks are not all brief resonances balanced at the edge of falling apart. Some may form genuinely bound additions to the hadron spectrum. Whether these deeply bound states exist exactly as predicted remains an experimental question. Their production rates may be small, and their decay signatures may be difficult to isolate. Yet the discovery of the doubly charmed tetraquark has already shown that 2 heavy quarks can participate in a narrow 4-constituent state. The path toward heavier and potentially more stable partners is now open. The deeper change concerns our idea of simplicity. Physicists often search for a small number of fundamental laws, and the standard model provides a remarkably compact set of particles and interactions. Tetraquarks do not add a new fundamental particle to that model. They use quarks and gluons that were already known, yet simple laws can generate complicated outcomes. A small set of quark flavors, interacting through one strong force, produces protons, neutrons, hundreds of ordinary hadrons, atomic nuclei, and now a growing range of exotic structures. The complexity does not come from adding new laws for every particle. It emerges from the many ways the existing laws can organize the same fields. This makes tetraquarks important even if they never become useful in technology. Their value lies in what they reveal about emergence. A proton has properties that no single quark possesses. A molecule has properties that no isolated atom possesses. A tetraquark adds another example of a whole becoming more than a list of components. Its mass, lifetime, and decay behavior belong to the complete arrangement. Change the organization, and the particle changes even when the flavor list remains similar. There is also a practical humility in this discovery. The old 2 and 3 constituent rulebook worked for decades because most known hadrons followed it. It was reasonable, useful, and incomplete. Tetraquarks remind physicists that nature may use every arrangement the laws allow, even when experiments have not yet revealed it. Absence of evidence can reflect instability, low production rates, or insufficient detectors rather than impossibility. A state may exist but decay into a crowded background. It may be produced only through rare processes. it may require an energy and precision unavailable to earlier machines. The expansion of the exotic hadron spectrum was therefore not caused by the strong interactions suddenly learning a new trick. The trick had always been present. Detectors and analyses became capable of seeing it. The next generations of experiments will sharpen this picture. Larger data samples from the Large Hadron Collider will reveal rare decays and possible partner states. The upgraded Bell experiment will study heavy mesons in a cleaner electron and positron environment. The BS3 experiment and future facilities can map threshold regions with great precision. Improved lattice calculations will connect measured states more directly with quantum chromodynamics. The most useful discoveries may not be new peaks. Precise measurements of known tetraquarks could be even more revealing. Small differences in mass may determine whether a state is bound or unbound. Ratios of decay rates may expose compact components. Production in different collision environments may indicate size and formation time. A complete picture will probably not assign every tetraquark to one rigid category. Some will be strongly molecular, others may be mostly compact. Several will occupy the middle, where quark level and hadron level descriptions overlap. The variety itself may be the final organizing principle. Tetraquarks changed what matter can be by showing that the familiar particle families were not the limits of confinement. Quarks can form more than mesons and baryons. Hadrons can become components of larger hadronic structures. A particle can contain several internal arrangements at once. The line between one object and two can depend on energy and interaction. They also changed what it means to understand matter. Knowing the smallest ingredients is only the beginning. The difficult question is how those ingredients produce stable patterns, temporary resonances, and entire families of structure. The objects around us are built from the simplest long-lived solutions to that problem. Protons and neutrons have survived since the early universe. Tetraquarks last for almost no time at all, yet both belong to the same story. Both are arrangements created by quarks, gluons, and the strong interaction. One forms the matter we live with, the other shows us what that matter might have been, what it can briefly become, and how many possibilities remain hidden inside rules we thought we already understood. So the tetraquark is not merely a particle with 4 quark constituents. It is evidence that nature's rulebook was always larger than the first page we learned to read. It tells us that the strong interaction does not build from one fixed design. It experiments with clusters, molecules, compact states, and mixtures, keeping only some of them together long enough for a detector to notice. And somewhere inside the next collision, among the tracks and energies recorded by instruments surrounding an empty point in space, another arrangement may already be waiting. Not a new ingredient, perhaps, but a new way for familiar ingredients to become matter.